How are you?
Hi.
Good.
Good. How are you?
Yes,
So
fine. Thank you. Yeah.
yeah, we start at 2 p.m. local time. Can
Okay,
you
thank you.
share your slides?
Yeah, let me just start in a second.
Sure.
Oh, and now my pointer is working, so it's good.
Yes. Yes, it works.
Very good.
Ah, 可以听到，没有问题啊。Okay, it's 2 p.m. Let's start on time. So today we're very happy to have Professor Cuvedo again. He's gonna give us a second lecture on string theory and cosmology. Let's welcome him.
Thank you. Thank you very much. Thank you, John. So, okay, let's continue. Just to remind you, this is lectures in string theory and cosmology, and I'm basing the lectures in two review, mostly this long review that appears in Physics Reports earlier this year. But also in the tales about model stabilization, which is a key part of the lectures. This other review is much more detailed into the calculations and so on. So anyway, so we have been discussing several aspects of string and cosmology. So just so far, we have been addressing what I call three related questions. One is model stabilization. That means to fixing the size and the shape of the extra dimensions that are also always present in string theory. And then to get the jitter, that means that you have to stabilize the moduli, but in a way that you have to get a potential such that the possibility there is a minimum of the potential. That means a stabilization of the modulus at a value of positive cosmological constant. And we have mentioned these scenarios, this KKLT and LVS that appear in type 2B string theory, that a combination of using fluxes, some branes, and non-perturbative effects and so on, allows you to get minima of these potentials of these fields that give you the Sitter space. And moreover, we found many of them because they're depending on a lot of integers given by the fluxes, and these integers give you numbers of 10 to the thousands or so of possibilities. And then with this formalism, not only addresses the challenge of getting the Sitter, which is we want the Sitter because we know that the universe is accelerating, but also the possibility to explain, quote unquote, why the acceleration is driven by something the equivalent of a cosmological constant to be very small, and the way this is achieved is by having so many solutions that at least one of them will be small, and that's not a trivial statement because the problem with the cosmological constant is not only getting something small, but it's getting something that is small after corrections from all the standard models contributions. So we know the Higgs field contributes to the cosmological constant a huge amount. The electron itself, the mass of the electron, give you a huge amount, which is already 15 orders of magnitude bigger than whatever we see. And with this approach, all that is taken care of because this finding a universe with a very small cosmological constant after all those corrections are done, because there's so many of them that you can just adjust whatever corrections you have into your minimum. So this is a non-trivial statement, even though people take it very softly in the sense that the anthropic word is mentioned and we don't want to have anthropic explanations. But as Weinberg used to say, we don't like these anthropic explanations, but why nature should care about the taste of physicists. So if we don't like it or not, that may be the way that nature has behaved. And as I said, this is the concrete implication of concrete use of string theory and cosmology, which I think should be taken seriously. And the third thing is that inflation, we wanted to get the early universe that the most successful scenario at the moment since 40 years ago is this inflationary universe for which there is a cosmological constant again, but a very early universe for which the universe accelerates very, very, very fast because the cosmological constant is much bigger. And but it has to change. That means a slow roll, and then at some point provide the stabilization to the minimum of the potential. So while this happens, what is doing the slow rolls, the universe accelerates, and at some point you produce the matter you have seen today, I mean the quarks, leptons, and so on. So this is the general picture for inflation, and what we have discussed, I presented to you several examples of inflationary scenarios that were derived by using modular stabilization, by just computing these potentials for the modular fields in such a way that you find the Sitter minimum like this, but also you find a region where there is sufficiently flat and high the potential that allows you to inflate. Okay, and these arrows here mean that there are fluctuations of the field, and these fluctuations are the ones that explain the inhomogeneities and temperature of the cosmic microwave background. So this is again very well in touch with experimental results. And I gave you a list of models with different predictions for the spectral index and the tensor to scalar ratio. And this is going to be tested. I mean, the spectral index has been very, very well measured, but the tensor to scalar ratio has not been found at all. And there are experiments running in the next 5 to 10 years that are again going to get closer and closer to test smaller values of this quantity R, and that will be a way to test some of these models. Okay. So now the next step is now I'm going to see what is the string theory can tell you in the moment after inflation. So in cosmology, we claim that we know everything from the time of nucleosynthesis, which is a few seconds after the Big Bang. And but between inflation that happened 10 to the minus, I don't know, 30 seconds or so of the Big Bang and nucleosynthesis, we don't know anything, and many things can happen. And so that's a room for string theory to have something to say. String theory say something after inflation and without changing nucleosynthesis, because nucleosynthesis, we know it works, so you have to get it to work. And there are several things that people have been doing over the years to to see how much string theory can say about the physics after inflation. So that's what I will discuss in the next few slides. And what happens is there are several possibilities, and I can illustrate it with this. In the standard picture of inflation, you have a field, the inflaton, that gives you inflation. At the end, it goes to its minimum, and in the minimum, it starts oscillating. And when it oscillates, it leaves its energy to create particles, and that's the particles that we see of the standard model, the quarks and leptons and so on. So this is the period people call reheating. So it's the same field that gives you inflation. At the end, generate all the particles that we see, and this is essentially in practice the Big Bang for us, because that's when all the particles were created. This plasma of standard model particles is created by the oscillations and decays of this field, given that they had a lot of energy during inflation, and that the energy is given back to produce particles and so on. So that's the standard picture without the string theory of inflation. In string theory, as illustrated in this picture, there are many of fields. One of them can be the inflaton, but there are many others. Whether we like it or not, there are many others because the space, the compact dimensions are very complicated, and they have many of these non-trivial cycles, so they have many moduli, as I said, there are hundreds of thousands of them. So the picture is different because one of them can be the inflaton, or one combination of them can be the inflaton, but the others are still there. And that's what this picture is trying to illustrate. So imagine this field that I call pi again, is not an inflaton. So while it is inflating, the other field is inflating. This minimum, this field, for instance, is trapped not in its low temperature minimum, but it's trapped at another position because the potential at that in that time is dominated by the inflation of the other field, the inflaton field. So then for this field phi, which is not an inflaton, it doesn't have to be in a minimum of the potential, but it can be in the natural thing is to be in another minimum because it's a different potential for itself. And so it is trapped during that minimum. When inflation finishes, then this field starts going to its real minimum until it ends here. So these are the stages that I just put here. Here, then it starts going to oscillate, then it oscillates fast and produce all the particles while it's decay. And then at the end, it just rests in its minimum, but the particles have been produced. So this changes completely the picture of reheating, because reheating, as I told you before, it was just assumed to be given by the same field, the inflaton field, that gives you inflation, give you reheating. Here, some field gives you inflation, and then the reheating is given by another field or several other fields after, many of those fields go back and go to the minimum. But it's the last field to decay, the one that is actually giving the reheating that we observe today. So essentially, with the string theory, you separate the two processes, the inflation from one field and reheating from another field. And that allows you to have the reheating temperature to be much lower than the inflation temperature, for instance. So, so it's totally different picture. So in this period, while the field starts oscillating around its minimum, it dominates the energy density of the universe, and that's what is called modular domination. And actually, in the past, when this was started to be discussed, this was usually called the cosmological moduli problem, because this field will tend to dominate the energy density of the universe. And if when it decays, it may ruin nucleosynthesis. So there was a bound on the mass of this field, not to ruin what we know, and not to overclose the universe or to ruin nucleosynthesis. And the bound was that the mass of this field has to be bigger than 30 TeV. And we were expecting these fields to be of the order of a TeV because of the hierarchy problem of particle physics. And and then that was considered to be a problem, a cosmological problem, because if these fields will have the mass of a TeV, which is the scale that LHC has been running, if this field would have been at that scale, then they will ruin the cosmology. So that was called the cosmological moduli problem. Now that we know that, for instance, supersymmetry has not been discovered at the LHC, so the mass of these particles can be heavier than TeV. So being a mass of 30 TeV is not a problem. So now, but it's a period in the history of the universe, and we call that modular domination. Okay, so the natural thing to have in string theory after inflation, a period of modular domination, and it is the last field to decay to be the responsible for reheating. Okay, so that is essentially that changes the picture of the history of the universe between inflation and nucleosynthesis. Okay. There are several ways of getting to this. But I put you the standard picture that people say. But there's a more dramatic proposal, a scenario that people can have considered. It's very recently, Conlon and company, in the last couple of years, they have been studying this scenario, which is called kinetic domination, in the sense that this is just a cartoon. You can have inflation at some scale, but then at some point the minimum is here, the late time minimum, so the today minimum is here, but it looks here is so small that you don't see it here. So I have to do a close-up here to say that there is a real minimum here. So the field starts here, inflation, then it runs a lot, but a lot of distance, say in the order of 10 times M Planck. And then at some point it goes into the minimum. This has the interesting feature is that you can have the scale of inflation very high, very, say, close to the Planck scale, or a few orders of magnitude, 2 or 3 orders, 4 orders of magnitude at the most. So the inflation scale to be very large, but the inflation of the standard model, given by the size of the field, can be very small. So imagine this field is the volume of the extra dimensions, or so the volume is very large. The scale of a string is very small because the scale of the string is M Planck divided by the volume to the 1/2. So the scale here will be small scale, say TV, and this can be 10 to the 17 GeV, for instance. So the grand unified scale, and this is the TV scale. So, and then you can have this long period of running. Since it is running a lot, the field is here was rolling slowly, that's inflation, but here is rolling very fast. Rolling very fast means that the energy, the kinetic energy dominates the energy density of the universe at this time. And that's what is called kinetic domination. Kinetic domination. So it goes very fast. But while you run here, there's friction, there's a Hubble friction given by the Hubble parameter. And then it avoids this overshooting. So the natural thing you say, oh, this may be pass through here and overshoot the minimum. But the friction is good enough to stop them and the minimum and then from the field to stay here. And then you have here your is a low energy scale for the standard model, whereas the inflation can happen at very high rates. Okay, so that's a scenario that's kind of natural to consider because high scale inflation is a good possibility, but low energy physics at late times, at our times, is also what we want. We want to have a TV scale. Okay, for that you need this field to run several times in Planck, not many times, but order 5 to 10 in Planck to change from the Gauss scale to the electroweak scale. Okay, so and once you get there, you have the period that I was telling you before of moduli domination, where the field decaying to its minimum and producing the particles. Okay, so okay, and also during that period after inflation, you can study dark matter and see which of the candidates for dark matter you can have that can contribute to the energy density of the universe today and to the matter density. And there are many candidates for dark matter, unfortunately. Fortunately or unfortunately, it's good to have many, but we cannot just put just one, which is the preferred. So the standard one, dark matter candidates are the moduli themselves. They are fields which are only coupled gravitationally, so they're candidates for dark matter. Actions, each of these moduli fields have a real and imaginary part. The imaginary part is a pseudoscalar, and their actions, they can be the QCD action, but it can be very light actions, 10 to the minus 20 electron volts or so, people call fuzzy dark matter. There can be WIMPs, weak interacting massive particles in the brain of where they live the standard model. People have even considered primordial black holes or anything in the hidden sector. Remember, you have a standard model living in one brain, and there will be other brains that are totally hidden from the standard model except for gravity. So anything in the hidden sector, like dark photons and so on, can be candidate for dark matter. So there's a rich structure of potential dark matter candidates. And as I say, it's good because there are many candidates. It's not that good because you cannot just predict in general what is the preferred dark matter candidate. But there's something that people usually don't talk that much about, which is dark radiation. So there are too many dark things. There's dark energy, that we talk, which is necessarily the cosmological constant, or a variation of it. Dark matter is just matter that contributes to the energy density of the universe today, and is dark because it doesn't couple to electromagnetic interactions or strong interactions. And and that's dark matter, and it's cold. It's called dark matter, so that means that they are not relativistic particles; they're heavy objects. But then there are light objects. We know that the photons is very light, of course, but also the neutrino. The neutrino is light, and the neutrinos are light, and they're also dark, but they will be hot dark matter, and they are not good for structure formation, so they're not the best candidate for dark matter. Um, and of course, in mainstream models, you have neutrinos. So, but this interesting thing is that there are other candidates for what is people call dark radiation. Dark radiation is any relativistic particle that doesn't see electromagnetic interactions. It can be dark photons, or it can be these ultralight actions that I told you, so scalar particles that are not charged, and they can be extremely light. And they are extremely light, they can be relativistic, and anything in the hidden sector. You can have photons in the hidden sector, which are massless also. They could be dark radiation for us. The interesting thing about dark radiation is that it's extremely constrained. People have a way, by the experiments that people have been doing with the cosmic backgrounds and others, it is parameterized by what people call the effective number of neutrinos. So this is delta NF, with the variation. So people have, by just using cosmology arguments, people have found that the number of relativistic, the number of neutrinos has to be 3 point something. It can be 3 points, a little bit more, but not 4, for instance. And so this variation between 3 and 4 is the quantity that people call delta NF, and it is contributed by any candidate for dark radiation. Extra neutrinos, one cannot be, but it can be other relativistic particles, and that constraint is very small. It cannot be delta NF is smaller than 0.2. As I told you, each neutrino contributes 1, essentially, and anything else you have, all these possibilities from string theory, from hidden sectors and everything, they have to contribute no more than 0.2. So that's a way of constraining the models a lot. You can kill a lot of models because of that. So it's good to see, because you can have candidates for that radiation, but it's a good, probably one of the best way to eliminate models which are not realistic, because they can give you too large delta NF, and that is experimentally very much constrained. Okay. The third thing that comes out also from this potential, you can see the potential give you a minimum, and then you see the fields oscillates around the minimum. But it is not just a harmonic oscillator oscillation, but it's a long oscillation. And because of that, at some point while the field is oscillating, it is producing inhomogeneities in space-time. And these are usually called oscillons or oscillatons. And they are not stable, they are quasi-stable. And you can have different shapes. These are just simulations, the people, and numerical simulations coming out of the KKLT or LBS scenarios. You can see these inhomogeneities very well defined here. And they can be formed. And at some point they decay, but they can be formed while the process of the field is oscillating. And they leave their imprint, and the imprint they leave is gravitational waves, because these things are not spherical symmetric. They have the different shapes. And you can compute the spectrum of gravitational waves that they produce. And for instance, for the KKLT, you have this spectrum. For the large volume scenario, you have this other spectrum. And they have different shapes, so that's a way of in principle, differentiate between the different models. So you manage to detect the gravitational waves. You can just see the spectrum coming in this way compared to the spectrum coming this way. You can see, oh, this is KKLT, or this is LBS, or could be something else. So in that sense, these oscillants are something that can provide measurable quantities, gravitational wave spectrum. Even though the spectrum is different for the different scenarios, the frequency when you compute it, is of the order of 10 to the 9 hertz in both cases. And the amplitude also changes a bit from both. So that drove some of us to explore the possibility how to detect gravitational waves of high frequency. Because you have seen that LIGO and Virgo, they have been detecting gravitational waves coming from black holes and the black hole mergers. And that's very impressive, of course, but it's just an astrophysical source and doesn't give you that much new information about fundamental physics, but it's just a confirmation that gravitational waves are formed and these objects are there, which is spectacular. But the frequencies are from the kilohertz to hertz, essentially. So, and now in the future, people are going to explore LISA, which is the satellites, and there's a version in China, that Taiji, I think, that will be very exciting also, that will be testing sources of gravitational waves at very, very small frequencies, nanohertz or so. But the study of higher frequencies, higher than kilohertz, is in its infancy. It's just starting to be reconsidered, and we have been pushing for that because I think that's a golden opportunity to test properties of any physics beyond the standard model, in particular string theory. So now there's a small community, people working on potential detectors for higher frequencies in the megahertz and gigahertz. And so I can tell you we had a white paper a few years ago, 2021, and then it appears on this Living Reviews. And the activity has been so much in the last 2 or 3 years that there have been, and now we're rewriting, since it's a living review, it will be a new version coming up in the next year or so, because there's a lot of interest in the community, independent of string theory. So, okay, I have to say that is the first time I write a paper with experimentalists in my life. And in this set of authors, only my collaborator Francesco Muye and me have considered string theory, and the rest are cosmologists, experimentalists, phenomenologists, and so on. And but now the community is getting bigger, and there have been workshops every 2 years, one in Trieste, ICTP, one in Cambridge, and one at CERN last year, and there will be more coming up. And that, I think, is a very promising direction. And it is promising because at high frequencies, there are no candidates, astrophysical candidates. There are no black holes or something that can primordial black holes maybe, but astrophysical black holes not, that can, or cause of neutron stars or anything. So whatever you will see will be either new physics at different scales, and early universe cosmology. So it will be stochastic gravitational waves coming in all directions. So, and so that's I find that probably for me, probably the most exciting thing going on. And yes, and maybe I'll say something here. For instance, I told you that we test everything beyond standard model. There's one source, only one source of where it's pure standard model, which is very good. There's a standard model, the plasma of the standard model. After reheating or something, whatever happened in the early universe of inflation or so, the plasma itself couples to gravity, and that essentially produces gravitons, and that give you gravitational waves, and that give you a very well-defined peak in the gigahertz region, or 100 gigahertz or so. And that's very well positioned. So essentially, you look for gravitational waves at that frequency, you are where to find something, because the standard model already produces that and only that. Anything else will be beyond the standard model. And there has been a trend in the last couple of years to compute the spectrum for this is beyond the standard model, to see how that changes compared to the standard model. And it so happens that the standard model dominates over almost everything, except if the source is our string theory, is a string theoretical. So string theory gives you a much bigger peak in a very generic way. So in that sense, that's a very tempting way to try to explore gigahertz frequency gravitational waves. So something is moving in the last couple of years, and I think this is very exciting. Okay, so just to summarize, we have an alternative history of the universe. The Big Bang we don't know, then inflation most probably. Then after inflation, we can have direct model domination, or you can have kination. And after any of those two things happen, um, then you have the standard radiation domination, matter domination, and the time today dominated by the cosmological dark energy. And we can see how the energy density of the universe changes here. It goes like 1 or 8 to the 6. So since A is the scale factor is expanding, this will dominate very shortly because then it will get smaller and smaller compared to the other ones, to matter, to the mobile domination, then radiation and matter. So essentially, that's a picture we can think, and all this is into consideration. So that's what I put question marks. Maybe there's more question mark on these two than on this, but still it's question mark. But at least it's to illustrate that string theory has something to say, not only about getting inflation, but also what happened after inflation. And there are plenty of things to be explored. Okay, so that was after inflation. Now, then what can we say before inflation? In principle, it's hard to say something because I told you Big Bang, we cannot say anything about Big Bang. However, and the landscape, you have all this minima, and our universe can be the outcome of a transition from one minimum to another minimum. And that was called vacuum transitions. So let me try to briefly describe vacuum transitions, which I think is very interesting. As I told you, we have this picture of the multiverse, where maybe I'll say this later. In the multiverse, imagine you have two minima. In the multiverse, we have many minima. But we have two minima. And so that was considered by Sidney Coleman and collaborators in the late 70s and early 80s. And that was a beautiful piece of work. It has nothing to do with string theory at the moment. So you have a potential with two minima. And just by standard quantum mechanics tunneling effect, you're sitting here, it will be the false vacuum. There's a probability that you can tunnel and then go to the true vacuum, to the smaller vacuum. Okay, this probability you have to pass. It's a tunneling effect that is very familiar for in quantum mechanics, and is very much suppressed. It's very exponentially suppressed, but it happens. It can happen. And so the process of doing that transition is that you have a region of the universe and your space, especially it just went from one minimum to another minimum, and that is the process of creating a bubble. So it's a bubble with a tension. Here you have a background in the false vacuum, and you create a bubble of the true vacuum in that region, and then they start expanding. Okay, and there's a wall that separates the true vacuum from the false vacuum, and that is the picture I was showing here. That's how the multiverse happens. You can create your minimum, your bubble, start expanding, then in that bubble you create another bubble, but in the other bubble you can be creating bubbles, and then there will be bubbles after bubbles after bubbles. And our universe will be one of them. So that could be, so the origin of our universe can be the decay of another bubble, of another vacuum. And the fate of our universe can be that at least a region of our universe can decay to another minimum. So that we can talk about before and after inflation. Okay, so in that sense, this could be the beginning and or the end of our universe. So our universe can be just one of the bubbles, and then at some point that bubble also decay. So it's worth studying. And I have to say that some small community has been studying this over the years, but it has not been totally incorporated within a theory of quantum gravity as string theory. And so there are attempts in different directions. And I will give you a little bit of history just for you to familiarize with the subject. And it started in earlier than 80s without gravity, but with gravity, Coleman and DeLucia, they studied this false vacuum decay in 1980. Actually, this actually was one of the motivations for Alan Guth to come up with an inflationary model in the early 80s, because it was precisely this picture of a different vacuum. Witten, in 1981, only 1 year after, he came out with thinking about extra dimensions about Kaluza-Klein theory at the moment in 5 dimensions. And when you look for solutions, there was a solution that would give you a bubble like this bubble, but instead of having inside a false vacuum, there was nothing. So no space-time, and the bubble starts expanding. So that's the bubble of nothing. It's one of these most scary papers of Witten, to say, because then the nothing expands and you have nothing, no space-time. And there's instability of the 5-dimensional theories people have been studying recently has been getting a lot of attention. Then in 82, 83, Vilenkin and later after that, Hartel and Hawking, they started talking about creation from nothing, or the wave function of the universe. So that is very interesting that you start applying quantum mechanics to the whole universe, and then you can consider the possibility of starting from nothing and then create the universe. So let's say you're computing with the instantaneous effects or something to have appear the universe out of nothing. And yes, that's still very, the Hartel-Hawking, the wave function of the universe is something that is very, very much in fashion recently. So, and then Brown and Teitelman in 87, they talk about more general things called bubble nucleations in general, not necessarily with the potential. And they provide a very nice formalism. Then Farhi, Guth, and Guven, they started talking about creation of the universe from the lab in 1990. Just start from the lab and just create the conditions for the appearance of a bubble of a false vacuum or something, and then the bubble expands. So you can create the conditions in the lab, in principle, to do that. Of course, that's very unrealistic, but in principle, to do it in practice, but in principle, they studied that approach. The result was not very much convincing because they need some instantaneous, which were singular, but that was approached by Polchinski, Fischler, Morgan, and Polchinski at the same time, more or less, after them, to do it in a Hamiltonian approach. All this was done in the Euclidean approach, with this in a Hamiltonian approach, and then they confirmed the results of Farragut and Guven. But this has been very much criticized over the years, and it's totally open if this is happening or not. This is only being reconsidered recently, and so there's plenty to be done. So there is something open in the formal aspects, I would say, is this vacuum transition. So this just give you a rough idea of what it is. You have the potential of the 2 minima, but Coleman does is just remember when you do tunneling, you have an oscillatory solution here, oscillatory solution here, and you have a decaying exponential there. And the decaying exponential is you can see that you change time by I time. So you can have exponential, you can change the parameter by I times something, you will get a decaying exponential. That motivated Coleman to consider a Euclidean first field theory and then gravity with imaginary time, say. And then that would consider just the potential. You just turn the potential upside down, and to study the transition from this minimum to this minimum, you study a motion from here, so a solution that will give you from this minimum to this other minimum. And I won't go into details. They find the solutions called a bounce that you go from here to here and then back. And it happens to depend on always in the combination x squared plus tau squared. So it has O4 symmetry for instance. Without gravity, with gravity he assumed that it's true. And then when you do the analytic continuation back to get Minkowski, they get a metric of this type for the bubble that is formed. And this metric, you can see it looks like a Freeman-Robertson-Walker cosmological solution with an open universe. So that is interesting because it has been into the claim that whenever you produce these bubbles, you have an open universe, and that will be a very generic prediction of this scenario, the landscape. So this Euclidean formalism, I find it a bit ad hoc somehow. What is the standard way of proceeding? You study these issues in Euclidean time, and at some point you change to the Lorentzian time. Then you do the expansion. And in the case of Hardell and Hawking, they did that. You can study that in terms the equivalent of the way of the Schrödinger equation for gravity is the Wheeler-DeWitt equation. And you can consider this in terms of a potential for now, where the variable is the scale factor of the universe rather than a scalar field. And then see you can, that would be a way of saying that you can create something out of nothing. In the landscape, you have a bigger picture of this. You have many potentials that are discretely, they are discrete, different, dependent discrete parameters, which are fluxes. So you have this potential, you have this potential, you have that potential, and so on. For each potential, you can always have the decay from the minimum to the runaway, to the, say, from the finite volume here to the 10-dimensional vacuum there. The same from here and so on. But you can also find the case from this to that one, from this to that one, for which there's no barrier of the potential because it's just different fluxes in the four-dimensional perspective. So people have been trying to study that. This transition here is the brown theta one, and the other one, the compactification, is the Coleman-de-Luce. And people compute the fluxes, the transition due to the fluxes, and it goes like e to the minus the volume square. If the volume is large, it's very, very, very much suppressed. But so that means it prefers to go to the decompactification than to go from here to there. And so there are several questions you can ask in terms of this transition rates. And I think for the sake of time, I will just give you just the general picture. You can, I mean, these are the relevant papers, Coleman-de-Luce. Lee and Weinberg also estimated the transition, not going from the false vacuum to the true vacuum, but also if you have gravity, you can go from the true vacuum to the false vacuum. And then you can have, you can go from the small cosmological constant to the big cosmological constant. And there's, the transition goes like e to the minus b, where b you can compute in terms of the action of the instanton on the background. And for some cases in what is called thin world approximation, people have computed what exactly this b is in terms of h square is the cosmological constant outside and hi square the cosmological constant inside, and you can just compute how much how big the transition is, and you have. Then you can start studying transition from de Sitter to de Sitter, de Sitter to Minkowski, Minkowski to de Sitter, and then some of them back from the small to the bigger cosmological constant. And so there's some techniques that have been developed over the years to compute these quantities. As I told you, there's a possibility of going from upturning from a small cosmological constant to a big cosmological constant, and you can study. You take the limit to go from Minkowski to de Sitter, and you do the naive limit, you get zero. The transition to be zero because you have to take one of these quantities to zero, and so e to the minus infinity is zero, and that would be the transition going up. But depending on how you take the limit is different. So this is taking Minkowski to be the limit of de Sitter with zero cosmological constant is a bit dangerous because the topology of de Sitter and Minkowski is different. So you have to be careful. There's another way of taking, let me see if I have here. Taking that limit is you start with a Schwarzschild, like a black hole, and then take the mass to zero. That will give you also Minkowski. And you do that, you get a non-zero result. And that's what Polchinski et al. Did. So essentially, that is very much into an open question. So it's debatable. That is recent. It's interesting because, as I told you, there are these general claims. So the standard law is the following. Whatever you do, it's a very complicated thing, but at the end, what you get, if our universe origin is from a bubble nucleation, then the universe has to be open. There is three possibilities: the universe being closed, open, or flat. The evidence is that the universe is flat, but it's flattened because of inflation. But you will be very able to make precise measurements at the very early universe. You can distinguish between being open, closed, or flat. And the claim here is that the universe has to be open. If there is any way in the near or far future to be sure that our universe at the beginning was open or closed, and if it is found to be closed, this statement will say then you can rule out the whole landscape. That is interesting because people claim that users having many solutions give you no predictive power. This is a very predictive power. It will tell you you can rule out the whole 10 to 1,000 models by just one measurement. But precisely because of that, people like me, we have been trying to question this conclusion, and that's we're still not completely sure if this is a general statement or not. So there's something to question it. The same thing is that the general law is that you cannot tunnel from Minkowski to the sitter, as I was telling you. But there's a different results depending on how you take the limit. So again, it's an open question to settle. So that's something is good. There are things which are not totally definitive, but the questions are interesting. So in that sense, it's good to point it out. I will skip this thing just to be. So just to summarize what we have so far is that the standard law is that you can go from the sitter to anything, to anti de sitter, to Minkowski, or to another de sitter, up and down. So the sitter is okay. Everybody agrees that this. From Minkowski, you can go to anti de sitter. That was already in the original Coleman de Lucha paper. But to the sitter, the general law says not possible. From anti de sitter, you can go to another anti de sitter, depending on how much is the tension of that ball, but not to the Minkowski or the sitter. So that's the standard law. And the universe is open. So what we have been questioning is these three things, and if the universe is open or not. So that's something, for me, I consider that to be an open question, and it would be nice to settle it. Okay. And the interesting thing, one is the creation of the bubble of nothing that we can say that existed. People like Brown and Darling came out with the claim that these two nothings are the same. You have to define nothing, and they have a very clear definition of nothing, which is an ante de sitter with the unbounded from below. So there is no minimum. At the minimum, get deeper and deeper and deeper until you get unbounded from below, and that's what they would call nothing. And then they have this picture here. So you have a minimum, which you give it an amount of fluxes, you have this minimum like that. You reduce the number of fluxes, the minimum becomes deeper and deeper and deeper and deeper until then it disappears. And when that happens, you have this the space-time splits up, and then you have nothing in the middle, and that's what the bubble of nothing is. And so creating something out of nothing will be tunneling from this infinite and to the sitter to something, so to another to the sitter or so. So tunneling from here to here. And interesting thing that we did a calculation and got precisely what people had found in the past, like Hartle and Hawking or Vilenki, to get transition, the creation out of nothing. And that I think is also curious and very interesting to explore, because that may be very deep when we talk about how can you create something out of nothing. I have to warn you that all of this discussion I told you about the vacuum transitions and so has no string theory input. Only the fact that string theory gives you all the minima, and that's it. For all the formalism, all the calculations, didn't use any string theory, and that's a very open question. How string theory can approach these things, being a theory of gravity, and that I think is an interesting problem. Okay, so before I finish, because I think I have a few more minutes, I gave you what is the standard approach towards cosmology from string theory, but that you derive inflation and then see what happened after inflation and so on. And the sense that you rely on having an effective theory to describe your cosmology, and that's has been is probably the most natural approach and so on, and it has been partially successful. But that hasn't stopped people from proposing different approaches. And I have to mention them just to give you a general perspective. And one of them is the string gas cosmology, proposed by Brandenberger and Waffa. It's one of the beautiful papers in the late 80s. And they found that there's a kind of a duality. There's from large radius to small radius. And then wherever you want to ask what happened at small distances, you saw the same thing that happened at large distances because there is a duality. And then they can study the behavior of the temperature. There's a limiting temperature and so on. So this is nice. People have been trying to study in terms of realistic scenarios. Nothing very concrete has come out of it, but it's good to keep that in mind. In particular, because they're one of the few that address even the dimensionality of space-time, because they say that the strings winding around some regions tend to stop from growing. And so you can imagine all the dimensions to be small at the beginning, and the strings prevent them to expand unless they annihilate each other. So once they annihilate, then those directions can expand. And they made an estimate how the efficient of the annihilation and the dimension has to be 2 + 2 is 4. And that's when you can have 4 dimensions emergent. That I think is a beautiful picture. It would be nice to have a much more explicitly concrete realization. We don't have it yet. Another contender was very popular 20 years ago. Now it's not that popular. It's called equatoric universe, cyclic universe, in which the potential is different from inflation, and you have a period of contraction and then expansion, and so yes, and then bouncing back again. So that's what it's called cyclic. It's a revival of the whole idea of the cyclic universe. Then something called S-brains and rolling tachyons. So there's when you have brain anti-brain inflation, for instance, there's a tachyon field that finishes inflation. So the cosmology of that field, and that can give you something interesting, and so on. Oh, there's this first concrete scenario is called the pre-Big Bang scenario of Gasparini and Veneziano, and they assume that we know only time, positive time, but you can extend the theory when you have a duality for the scale factors in the Freeman-Rosen-Walker cosmology, and then you can talk about the time, negative time, and there's a duality between the two, and then you can try to see what happened in the Big Bang, what we call the Big Bang here, and they have to say, well, there was a very explicit scenario that they push for it, and then they even study the possibility of gravitational waves and so on. So I think they were pioneers, and it's always nice to keep that in mind as a totally different proposal. And well, I mentioned the bubble of nothing of Witten, and this is the standard inflation that I just used here just to compare with the other ones. So inflation is the standard approach, but we have to keep an open mind that there may be other ways to describe a string and cosmology. One thing that I have always emphasized, all this inflation so on is using effective field theory. And string theory tells you something which is very, very important and very unique for string theory. The fact that you have a tower of states in string theory, master states, infinite tower of master states, at some point you have an exponential growth of states at a given energies, and that will give you a critical temperature, which is called the Hagedorn temperature. And that Hagedorn temperature can be a finite ultimate temperature you can have. So that will have something to do with the Big Bang, but also can be a phase transition to another phase of string theory that can be more simpler. So studying of this Hagedorn transition, I think it should be very important in order to have a better picture of cosmology, more stringy. And just to finish, there are also the Swammland conjectures that people say, oh, the landscape is huge, there are many solutions and so on, but there's a bigger numbers of effective field theories which are not derived from string theory. So not all field theories can be derived from string theory. You can have different Lagrangians, different couplings, and so on. And the question is how to eliminate in a systematic way all of those and just keep the one that string theory gives you. And at some point when you go to higher energies, just to get to the string theory. And it is a very active subject in the last few years using conjectures, they call Swammland conjectures, to eliminate some possibilities. So one is the distance conjecture, how large the field range is for field for in string theory. I was showing you that in one case we have a field running from up to 10 times the Planck scale. That's still allowed, but many more thousand times we cannot have, because that will imply that an infinite tower of massless states will come up at low energy, and you cannot trust your effective field theory because all these fields will be equally light as the fields that you consider, for instance. So this puts a bound. There's this one that has been the strongest and less convincing. Is called the Sitter conjecture. People say, oh, it's very difficult to do the Sitter, so let's conjecture that there is no de Sitter. And that will be a dramatic thing because it kills the whole landscape picture because of the claims on the Sitter. The arguments about that are just that since it has been difficult to get the Sitter in a fully controlled way, then there's a chance, there's a possibility that there is no de Sitter. It's totally open, and I'm very much against because I think that we can trust enough what we have, but as in principle, people have been considering that seriously in the last few years, and that's something to keep also in mind. And there are other ones that I may not have time, the Transplanckian censorship conjecture, the cobordism conjecture. I personally like in the sense that you have two manifolds that are can be considered the boundary of a higher dimensional manifold. They will be equivalent to each other, and there will be a global symmetry among them, but string theory tells you there are no global symmetries. So then you have you cannot have that possibility. And so that is mathematically understood in terms of cobordism. And so that means that you have a manifold here, you extend it, it has to end into something. It's like an end of the world brain. And that may have interesting implications for cosmology. I think that this is yet to be explored more. So there's plenty to be done in this direction. And just to finish in terms of the Sitter structure, you say, imagine there's no de Sitter. So what is the alternative? The alternative is there's quintessence. There's nothing wrong with quintessence. It doesn't solve any problem, but it can be a possibility. And it would be interesting because you can measure the difference between the Sitter and quintessence by this quantity W that I told you was the equation of state, P over rho, which is minus 1.0 something now. If it is exactly minus 1, is the Sitter. If it is not minus 1, it can be quintessence or something else. But I mean, just to make the case that quintessence is different from runaway. Runaway is very generic, but quintessence needs a very particular runaway. And that is at least as difficult to get as to get de Sitter. So if the argument of not against de Sitter is because it is difficult to get, quintessence is equally difficult or more. So in that sense, it doesn't address problem, but you have, again, to keep an open mind because that's experimentally, that would be very nice if we can see that there's a deviation from the standard lambda CDI model. And here are some of the papers people have been working in the last few years. So to conclude, so the moduli fields are the key things to study cosmology from string theory, and they're low energy remnants from string quantifications. That I think I see is a plus. Because people say, oh, inflation is very good because it dilutes everything you have, monopoles and so on, which is solve many problems. But it may be, if you have inflation, that you can also dilute any higher energy feature from a string theory, and then you will never be able to test string theory. But the moduli fields survive at low energies, and they're the fields that remain light in string quantifications. So they are the best way to confront the string theory with experiments in the future. So that's important to have that. There are inflaton candidates, or concrete models of inflation, which are people have been computing, and then can be tested experimentally, which is very good. The post-inflation cosmology can be changed from what the standard one because of who is the one who does the reheating. Then you have periods of kinetic domination or nodal domination changes the cosmology. There is the string landscape can actually approach the problem of dark energy, which is you cannot just neglect it. Is the concrete scenario that actually addresses the biggest puzzle that we have in nature. So in that sense, it's something to be taken seriously. There are vacuum transitions that we explore. The ultra high frequency gravitational waves for me is the future. So this is for experimentally minded people. I think this is the most interesting thing going on. And many open questions that I just listed here. So, okay, thank you very much.
Okay, we thank Professor Quevedo for the very pedagogical overview. Any questions? No? Is it very clear? Yes.
Professor, thank you. Thank you
Yeah.
for your nice talk. I have a nice question about kination. In your talk, you said that during the kination and the inflaton rolls down and for me, and this it seems to maybe encounter some questions about fine tuning because at the when the inflation stops, the minimum is far more the structure is too small compared to the whole potential. Or maybe I
Oh, no. I think, yes, thank you for the question. Yes, so no, I think, well, first of all, what I was presenting was a cartoon. So it can be one field being the inflaton, and then this is another direction. So in that sense, there's no fine tuning in that sense, because of course, it was just a cartoon, so I put everything in one direction. But just so you say, one field, the inflaton, you have inflation finishes, and then at some point to finish inflation, you go through the fastest road and direction, and that will be in another field direction. And that field doesn't have to be slow. The natural thing is to be fast, and then you have this fast rolling, and then it can be, for instance, this field, the inflaton can be a brain anti-brain modulus, so it can be inflation, then you finish inflation, and after finishing inflation, then the volume, while you're inflating, the volume modulus will be fixed at some particular value, say 10 to the 6 or so in Planck in string units. So that's when inflation happens, the two brains approach each other. Then when they annihilate, then the potential for the volume is modified, because now all the contributions from the brain inflation field disappear, and then you can have just the standard potential for the volume, and then you can have naturally, for instance, the large volume scenario precisely gives you that. Then the field going to its real minimum, which is much more bigger, 10 to the 9 or something, but I mean several orders of magnitude bigger than the value of inflation. And then you get the minimum. So in that sense, there is no fine tuning in getting that. And I think that the break inflation is a concrete realization. And the danger, as I said, will be that you overshoot that minimum because you are coming from high energy very fast. But thanks to the Hubble friction, then people have done the calculations, and you get it to stop in the minimum, and then you have the two things realized. You have high scale inflation and low scale fields. That I think is something I would like to emphasize, because probably too young to remember, but in the late 1990s, there was this proposal, the Cunningham-Eddy-Mopperson Valley with large extra dimensions. And then you can have the extra dimensions such that you have the fundamentals theory could be, the fundamental scale could be 1 TeV. And so people say, well, that you have 1 TeV as your fundamental scale, and we know there's a lot of evidence for inflation happening at 10 to the 15 GeV or so. So how can you explain that there's this higher energies if the string scale or something is 1 TeV? And so this kination scenario I told you is a way to answer that question. You have the volumes take different values while you inflate than after inflation. And so the volume can be small while you inflate, so that the scale of a string theory can be large. Because the string theory is scale is m Planck divided by the volume to the 1/2. And after inflation, then the volume can be much larger, and then the string scale can be much smaller. And so I like that because it's a way to have both things, the large extra dimension scenario consistent with inflation.
Thank you.
Any more questions? No. Okay, if no more questions, let's thank Professor Cueto for the 2 great lectures again.
Thank you. Thank you very much.
Thank you much. Thank
Thank you,
you.
Jindal. Thank you. Nice to meet you.
Sofiana, thank
Bye.
you.
Bye. Bye-bye.
And that's good to see you. Hope to see you next year. Bye.
Yes, me too. Yeah, bye. Regards to everybody there.
Okay, let's take a few-minute break. We are preparing for the next lecture. Professor Hong Liu will continue his lecture on the geometric origin of Yang-Mills theory. Let's welcome him.
Okay, last time we discussed the failed attempt by Pauli try to explaining the high dimension, trying the geometric origins of the Yang-Mills, particularly the Yang-Mills of the orthogonal group as the isometric group of the spheres. And we have successful examples like supergravities, 11-dimensional supergravity can be consistent reduced to a 4-sphere or 7-sphere, and we also have unsuccessful cases where a generic high-dimensional theory is inconsistent to reduce to the a sphere. So then here we would like to discuss, how to tell. How do we know when it is consistent and when it isn't? I think you don't have any battery. Yes,
You're right. Yeah.
but I can use this, I guess.
No. Doesn't work.
Oh, okay.
Yeah. Okay. I will ask them to change the battery. We just.
Okay. Yeah. Okay. So, as we have mentioned earlier, if there is a group action on the matrix so that all the modes are singlets, then the reduction is guaranteed to be consistent because the singlets cannot be as a sole source for the non-singlet modes. So if we consider this kind of metric, and that's where the sphere is is undisturbed, then it is clear that the breathing mode is singlet, and typically the breathing mode, in fact, is a massive mode in supergravities. And then this kind of reduction, and it's guaranteed to be consistent, but we should not consider this kind of trivial cases. We're interested in the SN sphere reductions and get all the SO n+1 gauge fields. This is in line with the Pauli's expectation, and we shall call this as a Pauli sphere reductions. I think the probably is better to call that not as a sphere Pauli reduction, but a Pauli sphere reductions. For torus and sphere reductions, which are maximally symmetric spaces, the number of degree freedoms are expect to preserve. For example, in 4 dimensions, we have 5 graviton modes, and the corresponding 4-dimensional Crookes-Klein theory would have 2 graviton and 2 vectors and 1 scalar, and totaling also 5 modes. Thus, we expect that there exists a flat limit if we have a kind of a consistent sphere reductions. Then we expect there is a flat limit such that the SN reduction reduced to the torus reductions. Now,
Forward.
oh, okay, use these keys. Okay. So we can look at the properties from the torus reductions, and the torus reduction basically have a very important property that is called the theory have these global symmetries, and in string theory or supergravity theory, these are called U-duality group, and they typically in the scalar sector they express as a G over K, where the G is a U-duality or global symmetry group, and the K is a certain denominator group. So the scalar form the coset. Then if we consider torus reduction, then want to try to say if I also have a consistent sphere reductions, then the sphere reduction, the Yang-Mills fields can be viewed as gauging the compact global symmetry group of SO n+1 that belongs to the denominator group. So then from this kind of argument, we will see some necessary conditions that the denominator group should contain this SON plus 1, the isometric group for the sphere reductions. Then in that series, in the torus reduction, then you have at least 1/2 n plus 1, a number of vector potentials or one forms, which is a dimension of SON plus 1. This is because in a previous lecture, we say if you want to gauge certain global symmetries, you introduce the corresponding gauge fields. But we want to say that the torus reduction and the sphere reduction have the same degree of freedom. We should not introduce additional new fields. Then the vector field should already exist in the theory in the torus reduction. So this is another condition. Then the remaining fields should form the representations of SON plus 1. And this is a very kind of a small amount of conditions, but turns out that provide very strong conditions to rule out many of the series of consistent sphere reductions. For example, if we consider pure gravity that we said that we already demonstrated it doesn't work. So pure gravity has a Minkowski vacuum, which can be written in this way. So the lower dimensional, if we reduce on this torus, then the lower dimensional vacuum is is conformal to ADS. So you can view that as a domain wall. So if the let's check if the sphere reduction, if it works, then the torus reduction should have a certain properties. Now, if we look at the torus reduction of n torus reduction, then okay, we start from thanks. So we start from the d plus n pure gravities. We reduce on this n torus. Then in this torus limit, the d-dimensional theory would have n number of Maxwell vectors, that is Kreutzmann vectors. Then there should be kind of n diatonic scalars. So these are the kind of the diagonal part of the GZZ kind of internal directions. Then there also, in addition to that, there will be 1/2 n minus number of axions. So the total number of scalars is the summation of this plus this, and they form a scalar coset, which is a GLNR of SON. So this is a global symmetry you always will have for any gravity theory reduced n torus. You will always have this global symmetry, but for pure gravity, that's all you have. And the dimension of that is indeed 1/2 n plus 1. Now you find that the denominator group here, SON, is a maximum compact group of this GLN, and this clearly is smaller than n plus 1, SON plus 1. So we don't have enough group, the compact group, in the torus reduction, the ungauged gravity series. So then you cannot really try to gauge this group to get SON plus 1. The symmetry simply doesn't exist. And this is a group theoretical argument why a pure gravity reduced on SN, it will not be consistent. Now, What about the successful stories? So consistent S4 reduction of M series. And we know that 11-dimensional supergravity has ADS7 cross S4 vacuum. If the S4 Pauli reduction exists, we would have a maximum gauge supergravity of SO5 gauge group. And the tallest T4 reduction of D equal 11 yields 7-dimensional maximum supergravity. And that, if you look at the field content, it has 5 number of 2 forms and 10 number of 1 form fields. And then you have 14 scalars. So these are the complete set of the bosonic sectors of the 7-dimensional maximum supergravities. And of course, for this 1 form, some of them coming from the metric, the Krug-Time mode, some of them coming from the dimension reduction of the 3 form of 11-dimensional supergravities. The same thing here. That so if we look at the 4 tolerance reductions, the guaranteed global symmetry, then you would have a GL4R. And because this is a special series of 11-dimensional supergravity, you get this supersymmetry enhancement. So that the global symmetry is enhanced from the GL4R to SL5R. So this is the UDR group of this. Now, this SO5 is a maximum compact group of this SL5R and is precise the isometric group of S4. So you see the kind of miracle occurs. If pure gravity, the dynamic group will be SO4, but now because of the 11-dimensional gravity, the enhancement of symmetry become SO5, which is the isometric group as S4. So if we start with ungauged, so this is from the dimension reduction point of view, but if I just say looking at the 7-dimensional supergravity point of view, so we start with ungauged supergravity and gauging this SO5 global symmetry. Our previous discussion in the field theory tells we would introduce SO5 gauge field. And there are precise 10 of them since the dimension of SO5 is 10. Sorry, I think I'm not familiar with it. But the supersymmetry does not allow us to introduce any new fields. We have to make use of the existing fields. And indeed, the theory already have these 10 of them. And the 10 is precisely the dimension of SO4. So those A mu, 10, 1 A mu basically form a antisymmetric tensor representation, which also is a joint representation of SO5. So the number is precisely correct. Then this, you also have a 2 form, have 5 of them, and they form obviously a vector representation of F5. So what is more subtle is these 14 scalars. How we would view that 14 scalars from the group of SO5. The S5 sphere can be embedded into 5-dimensional Euclidean space like mu I, where I equal to 1 to 5. And the round 4th sphere and its scalar deformation. So this is the round S4. And if we consider the scalar deformation, then the most general structure will be taking this form. I also write this exterior derivative to this covariant exterior derivative so that we can see how the gauge fields enters in this metric. And we also would insist that the volume of this sphere should be fixed. So the determinant of Tij equal to 1. that the scalar forms a symmetric tensor representation with a unit determinant. Now the symmetric tensor representation, because the total number is 5, so you 5 times 6 divided by 2, that will be 15 number. Then the determinant equal to 1, then 15 minus 1 is precise 14. So that precise taking care of these 14 scalars. So everything fits perfectly, and indeed the S4 reduction is consistent. Of course, these are all numerologies, and this numerology basically provides only necessary conditions. Because this, for example, this the actual answer is much very subtle, and I'm only going to present later with a simpler example. So in this talk, I'm only going to talk about the numerology like this. So consistent 7-sphere reduction of 11-dimensional supergravity. So D equal 11 supergravity also we know have ADS4 plus S7. So then in order to check if S7 reduction is consistent, then let's look at the 7 torus reduction, which give rise to the 4-dimensional maximum supergravities. And that has 28 Maxwell fields and 70 scalars. So these are the total number of the bosonic sectors. And the scalar sectors form a coset of E7 over SU2 coset space. So the denominator group is a maximum compact group of E7 plus 7, and this SU8 contains this SO8. So at least we know that we can have a SO8 to try to gauge it. And the dimension of SO8 is 7 times 8 divided by 2, so that is 28. So that's the precise number of the one-form gauge field that the theory actually have. So this gauge field form an adjoint representation of SO8, that is the gauge fields you need. So we can make use of the existing 28 one-forms as the SO8 gauge fields. But how about the 70 scalars? And how the 70 scalars organized in the SO8? Then as the sphere reductions, the round sphere, you must have this form. So, and you must have a Tij to do with it. So that is a scalar you must have in any kind of this kind of sphere reduction. And so this you must have this Tij, a symmetric tensor with a determinant equal to 1 for this 7th sphere. And 7th sphere embedded into Euclidean space, the indices running from 1 to 8. So it's symmetric, so 8 times 9 divided by 2 and then minus 1, and that's precisely 75. Now it will be very difficult to find out what's the other 75, because the total number is 70 scalars. Actually, I didn't immediately recognize how to find out the other 75. So I called Zhao Long Wang at Northwest University, and it seemed too easy for him. So the remaining 35 scalars form a self-dual 4-form representation of SO8. So SO8 is like 8 dimensions. So you have 8 indices here. So you can construct anti-symmetrical 4 forms. And that you find the total number would be equal to 70. Then you impose these self-dual conditions. Then that gives you the 75. And that one can also easily see where these 75 coming from, because if you look at torus reductions of a 3-form, you would get AIJK, and that's precisely 75 of them. And so you promote index 0 or 8 to get this four form. So anyway, so the number again fits precisely, but
The 35 scalar, they form a four-form representation.
yes, as a self-dual four-form representation. And you can see that this seven-sphere reduction actually, the ansatz was initially constructed by DeWitt and Nicolai, and that is some 87, a long time ago, but they didn't complete the whole story. And I think it's later by probably their students, kind of Nastas Vorman, and they eventually got everything correct. And the difficult part is really how to take this kind of these 35 scalars into the ansatz, because you can see that the 35 scalars of this Tij is very simple. It's just Tij d mu I d mu j. So that is easy to embed, but this set of 75 scalars are difficult. But it's not entirely kind of surprising if you look at the field strengths, actually the four-form field strengths. So one can relate this to the four-form field strengths. So now if we look at the 11-dimensional supergravity on the n torus and the corresponding U-dual group, and to see if we can find the corresponding sphere reductions. Again, this is not guaranteed, but we can play the numerology. If the numerology doesn't pass, then you don't even have to look at it. So these are the 11 dimensions reduced on various dimensions, and you can, from here you see that this group, denominator group, simply not big enough for any sphere. So the first one has to come from this O3, that is a two sphere. And so this seems to suggest from 11 to, you don't have a two sphere. So this seems to suggest that 10-dimensional supergravity you can consistently reduce on a two sphere, but you have to look at other parts as well. And this is the one we talked about. This precisely leads to the three-sphere reductions. And the sixth dimension, then if from 11 we would want to five-sphere, and that would be SO6, and we simply don't have that. So this seems to suggest that you can have a four-sphere reduction, but not from 11, but can only from the 10 dimension, because 10 to 6 you have a 4 dimension. But then this is not surprising. This would guarantee to work, because I already this is already working. So this one reduced on circle reduction will be equivalent as the 10 dimension reduced on S4. So that is not surprising. So another non-trivial example is 5 dimension. We know we have ADS5 maximum supergravity coming from the type 2b supergravities. So from the type 2b supergravity point of view, we want to check on the SO6 whether those fields would make any sense. So the scalar coset is 42, and the vector fields you have 21. So first, this SO6 is smaller than the denominator group, and the total fields in 5 dimensions is 21 one-forms and 42 scalars. To gauging this SO6 requires 15 gauge fields. This leaving 6 one forms, which can be due to the 2 forms in 5 dimensions and form a vector representations. So anything to do with 6 we will be happy because it's SO6, so it's a vector representation in 6. So we have 21 one form. We can split into the gauge fields of SO6, and then together with fields that form a vector representation. While the gauge field SO6, of course, they form a joint representation, right? So 21 would be equal to 15 plus 6. So that works. How about 42 scalars? 42 scalar basically this Tij, you need you have any symmetric tensor with a determinant equal to 1, and this gives rise to 20. Then you have another 20 that is antisymmetric 3 forms. And then you have 2 singlets. 2 singlets basically in type 2b supergravity, we know we have an SL2R S over SO2 coset space, the complex scalar. And they obviously have to be singlets under the sphere reductions. So that everything works perfectly as well. So the maximum gauge supergravity in D equal to 11 then can come from the consistent S5 Pauli reductions of type 2b supergravities. This again is just a numerology. Try to work out explicit ansatz. It's not easy to do. And these, of course, are well-known examples. And you say, can we use these kind of numerologies to get something as a consistent sphere reductions without previously didn't know about those things? So here, let's consider bosonic string theory reduced on torus and sphere. And the string theory have a signature duality, namely the target space-time duality called T-duality. And this morning, Jianxin talked a lot of it. And the string theory reduced on Tn has SO n, n global symmetry with a scalar coset given by that. Now, when n equal to 3, well, if you just look at that, then you will find that if you want to replace Tn as Sn, then it requires a group as SOn plus 1. And we don't see that as a denominator group. So, but n equal to 3, then something miraculous happens because SO3 cross SO3 just happened to SO4. And SO4 is just the isometric group of S3. So this same set tells us that if you reduce on T3, then the coset space was this. Then we can gauge this denominator group, and the resulting theory, it is possible to get it from the 3-sphere reduction of the bosonic string theory. Now let's look at the other fields. So the scalar coset seems to working. So the 2 form, if we reduce on T3, then 2 form you have 1 2 form. And 1 form, you have 3 Krutz-Klein modes and 3 winding modes. That's the standard string reductions. This add up to 6. And scalars, you would have 1 dilaton. This dilaton is a string coupling constant. So that is then plus 9 of this coset space. So 6 is precise dimension of SO4, forming the gauge fields under the gauging. And the dilaton and the 2 forms are singlets and the SO4, while the 9 is precisely this Tij metric, because SO3 and I and J, this is running from 1 to 4. So that means 4 times 5 divided by 2 minus 1, and that's precise 1. So this suggests that it's consistent to perform S3 Pauli reductions of string theory in any D dimensions and obtaining SO4 gauge group. So that was analyzed before this ansatz was working out and explicit, then we did find out this is indeed consistent, and we will give the explicit ansatz for these consistent reductions. We basically said that S3 is special. There's another case of a special case is that if you reduce a bosonic string all the way to 4 dimensions, 3 dimensions, in other words, you reduce the theory on D-3, or in that case, then once the theory reduced to 3 dimensions, of course, you would still have the string target space-time duality. However, the Krutskine modes and the winding modes you obtained are 2 forms in 3 dimensions, which can be due to scalars in 3 dimensions. So when these scalars add up to the cosets of the string theory here, then you suddenly find that miraculous things happen. The whole global symmetry is enhanced from the ODD group to OD-3, D-3 to OD-2, D-2. So there is an enhancement of symmetry. And the enhancement symmetries make the denominator group also enhance. Then this OD-2 is precisely the isometric group of SD-3. Because the isometric group, the SON, SN, the isometric group is SON+1. So here you don't see anything. You don't have this isometric group SD-3, but once get enhanced, then you have this. Of course, this kind of thing only works as a string theory. If you just write in a bosonic Lagrangian, you don't have these kind of properties. So once in 3 dimensions, then everything is scalars. You don't have a 1 forms or 2 forms. So the dimension of the scalar coset is D-2 square, and so you have a D-2 square number of total scalars. And the gauge group of SD-3 reduction is SOD-2, and its dimension is given by this. And this, of course, is only part of the total scalar. So let's look at the remaining scalars. Then this Tij, the dimension of this symmetric tensor with determinant equal 1 is given by that. And so if you add them up, then you add this 1. And this, in that sense, you add this 1 is like you don't impose the conditions of this Tij, basically. But you can impose the determinant of Tij and then use this 1. And this 1 basically is a singlet of SOD-2, which is a breathing mode of it. So again, from here, we will say this numerology suggests that there is a consistent S3D-3 reductions. And based on this, then we also find the explicit reduction ansatz can be constructed. So now let's look at pure gravity on T3 and then consider S2 reductions. As we have mentioned that there's no consistent SN Pauli reductions on pure gravity. Since the scalar coset of Tn is given by this, we just don't have this SON+1. However, when n equal to 3, then we have GL S3R over SO3. And SO3 is isometric group is S2. So the T3 reduction of pure gravity gives 3 Krutskine vectors, and the dimension is equal to 3. So considering the fact that S3 is a U1 bond over S2, the above numerology suggests that any Krug-Klein theory from S1 reduction of pure gravity can be consistently reduced on S2. This is related to the miraculous properties of S3, which is not just a coset, but also a group manifold of SO3, which of course is isomorphic to SU2. So the SO3 on one hand is a coset, but this also happens to be a group manifold. So S3 in a sense is much simpler if we regard that as a group manifold. So I'm going to have some review of this group manifold. Any questions so far?
There's some special reason why you only consider Tn and Sn. I mean, can we be more open-minded to consider some more exotic manifold or some combination? Let's say Tn times Sm.
I think you could consider more, and in some sense, our unfinished project, ongoing project, is try to consider some kind of neither torus reduction nor sphere reduction, but so-called T11 reduction. T11 is a certain compact space, right? But for here, we are only going to consider the sphere reduction and the corresponding torus reductions, right?
And the end relation with the in the literature, the Calabi-Yau commodification.
Right. So of course, Calabi-Yau, you don't even have a metric, so it is difficult to talk about the consistency of this.
But sometimes, let's say 3-fold, the compact 3-fold, we have either T3 or K. We have K3, right? Sorry, the 2-fold we have.
If you consider non-compact space, yes, but typically we want to consider the case where you have a gauging kind of. So if you consider, well, if you do have a non-compact space, and it's hard to convince that this is a lower dimensional theory, right?
Mm-hmm. Yeah, that's not people usually doing Calabi-Yau commodification.
Right, but yes, right. So, okay, my time seems to be not have many left, so let me try to. So this is a 3-sphere. Many of you probably know 3-sphere as a rotation group of S2. The rotation, the orthogonal SO3 algebra is generated by these polymatrices, and consider group element which given by these 3 Euler angles, which is a unitary with a determinant equal to 1, then one can construct around the 3-sphere metric, which write as a trace of G minus 1 dg, G minus 1 dg, and you find the metric is given by this. And this is precisely metric around 3-sphere, but written as a U1 bounded of S2. If it's a 3-sphere, then one can actually embed it from the 4-dimensional Euclidean space with a unit radius. And we can write these coordinates, Cartesian coordinates, in terms of compact spherical polar coordinates. And the 3-sphere, that is written as a foliation over U1 cross U1. And if you make a coordinate transformation, then this metric would be precisely the one you obtain from this group manifold. So this is how you translate this group manifold metric to something we are more familiar with as an embedding of the Euclidean space. And the metric is given by this, and one can easily see that this metric is invariant, and left and right group actions, because if you substitute in, you can trace around, and this Lagrange is invariant. And where these two transformation elements are constant SU2 group elements, so this add up become SO4. And the one form, one can describe, you can consider one form written as G minus 1 dg or dgg minus 1. One is called the left invariant one form, and another is a right invariant one forms. And so these are the properties. And so the whole group will have SO4 symmetries, but if the symmetry can be kind of broken from SO4 to SU2 by consider these kind of deformations from the round sphere to some kind of different different kind of distortions. Anyway, the U1 one form DZ allows one to embed U1 gauge fields in the metric, as we see earlier as a Kreutzklein theory. And the SU2 left invariant one form allows to embed in not the whole SO4, but the subgroup of SU2 YAMUs. Basically, you have a sigma I. Now you can have add a GI. Then the ordinary exterior derivative can be replaced by the covalent exterior derivative, and then the theory base the one forms and its theory is given by these properties allows to write NZs embed SU2 gauge fields in a much simpler manner. So, for example, we talk about S4 reduction of the group SO5. This is very complicated, but it has this SU2 subgroup. And the reason we look at SU2 subgroup is because the maximum supergravity in 7 dimensions is n equal to 2, and we can truncate it to n equal to 1 gauge supergravity, and which happens to be SU2 gauge group. And the embedding of SU2, we see that can be understood, can be embedded in a 3-sphere. And the 4-sphere the 4-sphere can be viewed as a foliation of a 3-sphere. So it's like a foliation of this 3-sphere, and this 3-sphere can be written as a left invariant one form, the sum of these. Then each of sigma I can put in the gauge field. Then of course I have to add whatever needed, the scalar fields, etc. And this eventually give rise to, this is a consistent Kreutzklein reduction essence, at least for the bosonic sector. And the substitute this into the 11-dimensional supergravity, we will get the 7-dimensional n equal to 1 gauge supergravity, where in addition to the usual supergravity sector, we know it also has the scalar potential, and this scalar potential have a fixed point such that the space-time vacuum is ADS. And the theory has a kind of peculiar called all-dimensional self-duality. So another example is consider 7-sphere reduction. The 7-sphere reduction, as I mentioned, it's a very difficult problem, and it took 20 or more years to eventually work out. But if one look at the SO4 subgroup, the reason we look at the SO subgroup because the maximum gauge supergravity is n equal to 8. And we truncate, so this is a typo, this should be n equal to 4. The truncation, the gauge group reduced from SO8 to SO4, and SO4 just happens to SO3 cross SO3. This seems to suggest that we can embed it 2 sets of left invariant forms of SO3, And the seventh sphere indeed can be viewed as foliation of S3 cross S3. You have one set of S3 and another set of S3. So those S3 then can again write as a sigma 1 square plus sigma 2 square and plus sigma 3 square. So this allows us to write the reduction in that, and it's a bit complicated, and eventually you got the d equal 4 and equal 2 gauge supergravities, which in addition to the SU2 Yamu's cross another SU2, we also have a complex scalars. And these are the whole. So I'm going to, of course, here, because this is a plus, this is a minus sign, this is a plus sign. That means if I set these two Yamu sets to be equal, then I can set the scalars to be 0. And the same with the axiom here. Once I do that, then I would get pure Einstein-Yamu's fields without any scalars, plus a cosmological constant. Of course, we know that typical people say that in supergravities, it's easier to get ADS space. It's more difficult to get, or probably impossible to get de Sitter space-time. But if you allow to the internal space to be non-compact, for example, like hyperbolic embedding, then we do have 11-dimensional supergravity solutions of this type, where the cosine now replaced by quarch, and this is actually a de Sitter space. So de Sitter space is possible, and it's a smooth embedding, except the internal space here is non-compact here. And one can also use this as a base, as a vacuum, and we can add in these Yamu's fields to be there. Then we will get the result. Theory would have Einstein-Yamu's with a positive cosmological constant. That means the de Sitter space-time. So Einstein-Yamu's with a positive cosmological constant can be also obtained from the 11-dimensional supergravities. With the price to pay is that the internal space has to be non-compact. So here we have seen so far the Yamu's can be indeed coming from the non-Yamu's supergravity theory in high dimensions via consistent Pauli reduction. This provides purely geometric origin of the non-abelian gauge symmetry. However, at the lower dimensions, that all the lower dimensions appear not to have the Minkowski vacuum. That is, my talk title is that I want to consider the lower dimensional Einstein-Yamu's in flat spacetime. Can Yamu's in flat spacetime also have a geometric constant, a dream of Pauli? Pauli stream requires a 6-dimensional theory that has a vacuum of Minkowski cross S2. Such a supergravity theory actually do exist, and this is called the Slamsevsky model. The Slamsevsky model basically is a 6-dimensional n equal to 1, 0 gauge supergravity with a bosonic sector given by this. In addition to the metric, you have a scalar, and this antisymmetric tensor B mu, then also have a vector. And in addition, you would also have this scalar potential. And this is a running scalar potential. You don't have a fixed point. So the 6-dimensional theory do not have a Minkowski space-time in 6 dimensions, nor ADS or de Sitter. And of course, another intriguing thing is that the cosmological constant is positive instead of negative. So this scalar potential do not have a fixed point, so it does not have a Minkowski vacuum, but it has a 4-dimensional Minkowski cross S2. And that is exactly what Pauli would like. So if he had known, well, he would not possibly know, because the paper is controlled 84. He probably died by then. So it turns out that one can have a consistent Pauli reductions and obtain n equal 1 Einstein-Young-Mills gravity with a complex scalar, and that was done by Gibbons and Pope. And the reduction at this is somewhat complicated, so I'm not going to give here. Do I? How?
A few minutes.
Yeah. Okay. So here I should discuss research reduction in a different context, making use of non-critical strings here. The reason is all my previous argument doesn't work anymore because you have a cosmology constant here. So if I consider Paulus reductions, the global symmetry, all this analysis no longer work because this breaks the global symmetries of a Paulus reduction. But nevertheless, they find the reduction inconsistent. So I'm going to, from a different angle, to look at this problem. The low energy effective action of non-critical string theory has an anomaly term, basically. If you look at this anomaly term, then this term looks very similar to the Salam-Sesky model. Although his theory is supersymmetric, while bosonic string theory is not supersymmetric. If you look at this theory, then it admits Minkowski class 3-sphere vacuum. Now, because if here this is like U1 bundled over S2, so if we reduce the vacuum on U1 fiber sigma 3, then we will get a lower dimensional is a Minkowski class sphere, and that's exactly the solution of the Salam-Sesky model if we consider proper dimensions. So the 3-sphere reduction of non-critical string with SU2, that is easily can be constructed by the argument we had before, and then the resulting theory is given by this. So for appropriate parameters, we can set this equal to 0, and this is precisely when d equal to 7. This was precisely the bosonic sector of the Einstein-Young-Mills theory obtained by Gibbons and Pope from the S2 reduction of the Salam-Sesky model. Now consider d-dimensional critical string theory, and if we do a dimension reduction, keeping the Krutz-Klein modes and the winding modes equal, then you find you got this d-1 dimension theory is given by this. And if you set d equal to 7, you got a 6-dimensional Lagrange. And this is precisely the Lagrangian of the Salam-Sesky model. So this seems to suggest that there is a very curious kind of duality between, at least in the bosonic sector, of a supergravity theory and a non-critical string theory that is not supersymmetric. And once one sees that, then the reduction index of the Gibbons and Pope would be straightforward, because the 3-sphere reduction of this is guaranteed, while the sphere reduction of this is also guaranteed because 3-sphere is a U1 bounded over S2. So you just extract whatever. Salam-Sesky model have the n equal 1, 0 supersymmetry. No, I'm only looking at the bosonic sector. The bosonic sector of the Salam-Sesky model is identical to the appropriate circle reduction of the bosonic string with a non-critical bosonic string, right? Yeah, but I don't know. But the point is that this allows me to obtain this reduction index. So, okay, this we have seen that Einstein-Maxwelli cannot be obtained from pure gravity, but the gauge symmetry can be explained via the Krutz-Klein reduction. Non-abelian gauge symmetry in curved spacetime can also have a geometric origin, but it's much more difficult to construct Yang-Mills in flat space-time geometrically. However, we do have an example of Yang-Mills in flat space-time that have pure geometric origins from the high-dimensional theory that does not have an abelian symmetry, namely the Salam-Sensky model. It suggests an intriguing, also our discussion suggests an intriguing duality between supergravities and non-critical string, at least in the bosonic sector. In our ongoing research, we find that using these dualities, we can construct a non-trivial vacuum solution in the hetero theory, which actually preserve supersymmetries. So that is a very strange thing. The solution is very unexpected. You would not think about that's why people haven't constructed, but we obtain it from a non-supersymmetric theory by through this kind of duality mapping to get a theory in heteros string theory. Then you find that the solution actually supersymmetric. So it's analogous to this relation between this to the Salam-Sensky model, which is supersymmetric. And the string origin of the Salam-Sensky model is not yet clear, and so our ongoing research is try to get a similar kind of approach directly from the 10-dimensional hetero string theories, and try to embed the Einstein-Yang-Mills theory in the hetero string theory. Not, of course, hetero string theory already have Yang-Mills. We don't use those kind of Yang-Mills. We only want to get the Yang-Mills coming from the internal matrix, right? Okay, that's all, right?
So we thank Professor Liu for the very interesting talk. Any questions? Yeah.
For the Salam-Sensky model, you have the cosmology constant that give you a theta vacuum?
No. It has a running dilaton.
Oh, running dilaton.
Exactly same way as a non-critical, you have this term.
Do you have the...
And this term turns out to be exactly same as the this term as a conformal anomaly term in this bosonic string, non-critical bosonic string.
I'm asking, do you have the vacuum solution?
The vacuum solution will be like a domain wall kind of thing, because you don't have a fixed point.
Okay, because of running.
However, it has this vacuum solution that is Minkowski 4 plus S2.
Okay.
Exactly what Pauli wants, right?
Okay.
And this, of course, is also supersymmetric vacuum, right?
Any other questions?
Professor, thanks for the nice lecture. And I have a naive question which may not be so related to that lecture. You mentioned the supergravity theory. I was interested in the supersymmetric field theory on the curved space-time. So usually when we talk about the supersymmetric theory, we have to specify the how to say that, a super Poincare algebra, right? So in the case of supergravity, how do we define the supercharge?
Well, I think what you are talking about, supersymmetry in curved space. Okay, if you consider supersymmetry in a flat space, then there is kind of a supersymmetry called a global supersymmetry. While supergravities are the local version of, like, gauging the global symmetry. So in the flat space-time, typical people talking about you got a supersymmetry. The two supercharge give rise to the translation, right? The Poincare symmetries. So now, if you localize the SUSY part, then you would also give rise to local version of the Poincare symmetry. The local version of complex image is just general coordinate transformations.
Okay.
But you can talk about in the supergravity, the pseudo transformation in the tangent space, where it's locally kind of flat. Now, in the case of you are more interested in this supersymmetry in the curved spacetime. It's still like the curved spacetime, but the curved spacetime is fixed, right? So this is a bit like a more complicated version of flat spacetime. So the pseudo transformation law in the curved spacetime, like ADS, it's still like global symmetries, while here supergravity is like local supersymmetries.
Okay.
Right. So that's the difference, right? But if you look at tangent space, then it's have the same super algebra as the one you talk about.
Okay, thank you.
Because of the time limit, we probably can have more discussions in private. Let's thank Professor Liu for these 2 great lectures again. Okay, let's again take a few minute break. We're gonna prepare for the next lecture. 因为我们在场都是中国学生，冯老师这2堂课就用中文来讲，因为冯老师这个 PPT 也是用中文来准备的。Sorry for some foreign professors. These 2 lectures.
You are expert, so I plan to talk in Chinese.
These 2 lectures are going to be taught in Chinese. Sorry about
You are
that.
expert, but I'm so sorry.
OK 好，那我们下面这节课非常高兴请到冯波老师。冯波老师现在是浙江大学跟北京计算科学研究中心的教授。冯老师当然是这个量子场论跟散热振幅方面世界级的专家了。其中 BCFW 这个公式，其中就是冯老师跟他的合作者一起提出的。好，那我们欢迎冯老师给我们讲课。
First, I will like to apologize to Paul. And when Jun invited me to give a talk, I said, okay, because I give a similar talk like last year for some school. So the transparency I prepare is full in Chinese. And today I see that most of the students is Chinese, so and also come from different backgrounds. It seems to me like if I use Chinese to explain things to them, they will much more appreciate and much more easy to understand what I will going to talk about. So that's why I decide to give a talk in Chinese. So apology to Paul. Okay, I will switch to Chinese now. 这2节课我要讲的主要是总结我们过去20年来在散热振幅领域的一些发展。这个发展呢，是因为是20年时间的一个非常深刻的发展，所以我肯定不可能在2堂课之间给出比较完整的解释。但是呢，我想把我们这个发展的最 critical 的 idea，告诉给大家。然后这个20年发展呢，主要是形成了一个所谓的一个新的一个这个散热振幅的这个研究纲领，就是一个新的研究领域。这个散热振幅本身实际上是大家学量子场论知道，这是场论中的基本的量，就是它是联系实验和理论桥梁。就任何散热振幅本身，这散热振幅这个概念是从量子场论或量子力学发展初期就已经有了在这里了。所以说我们从学量子场论开始就一直在算散热振幅，大家也知道费曼图。但是呢，就是它是用在量子场论中各个方向，比如高能物理啊、微象啊、实验啊各方面 collider field 都在用。但是呢，把散热振幅本身作为一个 object 来 study， 它实际上是不是特别多。这个一个短暂的时期，在1960、70年代的时候，当时强相互作用还没有确定是由阿贝尔光场描述的时候，当时有个branch 叫 S matrix model， 它是通过烟散振本身来确定强相互作用，就是我不要这个拉格朗日的描述，我直接通过一些一般的这个要求，比如物理的对称性、洛伦兹不变性、腰正性等等一般要求，我来约束这个散热振幅什么样的东西。然后我留几个参数，这几个参数通过实验 data 的 fit， 然后我就可以理解强相互作用当时 collider 产生各种这个散射截面，它关键思想是这样的。但是呢，这个 S matrix program 在大概几年之后就被菲尔布观察场取代了，所以这个 program 就基本上就大家没有太多人关注，一直到2023年开始 ，Witten 的一个文章就把散热振幅作为一个单独的 object 的研究，这个带到了给大家的公众的视线。所以过去20年的研究实际上就基本上在做这样的事情，就是我们现在这个一个新的领域，它就是 S matrix reloaded。这个 reloaded 就是来自于60年代当时这个 S matrix program reloaded 的一个意思。好，这是什么是散热振幅在这纲领的目标 object？ 为什么我们说这个是一个非常重要的进展？就这个进展是来源于我们用费曼图去计算散热振幅的话，对 HC 面临的这个科学目标，它是效率是远远不够的。就是 HC 要求的高精度的计算，用费曼图去计算的话，是我们算不了了。就是即使用超算去算，我们很多也算不了。就是你一个计算过程，你可能要算1-2年，那就没人愿意去做这样的事情了。那所以说，我们目标就是发展一个保守的角度，是发展一个费曼图计算的一个替代方案，这是一个目标。 但在这个目标之中呢，我们发现，我们通过发展各种新的思路和技巧，计算产生整幅的话，它反过来教给我们对量子场的理论本身的一个更深刻的认识。所以它一个长远的目标，就是比较宏大的目标，就是寻找一个有别于你们在量子场的教科书中学到通过拉格朗日量建立整个系统框架的一个新的框架方式。所以这个框架方式就是叫量子场的新形式理论。这个尼玛阿卡尼哈梅德还有他的合作者一直在鼓吹的这个 geometry 这个 amplification 这之类的，就是在这个路上的一个尝试。但是这个 ultimate goal 这个宏大的目标呢，它实际上是还非常远，就是我们现在只有冰山之一角，我们完全不知道这个最终是什么样的形成。string theory 可能是一种这个从某种意义上是一种量子场的新的形式理论，在这个意义上来说。所以 string theory 也是这种宏大目标的一个尝试。这是我们在跳纲领，它是这个从小的和大的说的它的目标。那么在跳纲领，它的基本特征是什么呢？它实际上是有几个特征。第一个特征就是在翘的角度，这是为什么我等会儿后面会说什么叫在翘。然后呢，第二个它是关键特征，就是散整幅解析性。这个在翘角度什么意思呢？在翘和非在翘 ，onshore 和 offshore， 就是你当时粒子的能动量满足爱因斯坦质能关系的叫在翘，它不满足叫非在翘，这是在翘和非在翘的这个区分。那个解析性什么意思呢？解析性从某种意义上 ，loose sense 就它是 everything considered to be complex space， 就是你把任何这个物理量都腐化，然后你定义在虽然我们散整幅是定义在实的失动量上。但是你把实的失动量腐化之后，你把散整幅考虑在定义在腐的动量上的一个函数，有理函数或者解析函数，就是所以说在这个意义上，我们说它研究它解析性。这个把实的腐化，这看起来像是一个数学工具，但它不是的，它实际上是有非常深刻的物理原因在里头。就是这个腐化这个本质，只有量子理论力学的本质，某种意义上它就是一个腐的。这句话很 loose sense， 但是它也是非常深刻的一个 claim 在这里。好了，那我们整个呢，就是希望通过后面的讲解来体现这个新的这个研究领域的这些特点。啊，我们接着再说这个为什么我刚才特别强调 onshore 和 offshore 的区别，就是我们的量子场论教科书的话，实际上你学量子场论的时候，我们就会知道我们实际上是会碰到两个关键的物理量。第一个物理图像就是一个粒子的概念，第二个图像就是场的概念。实际上粒子和场这个从这个量子力学一开始建立就在打架，到底是粒子是基本还是场基本，一直在争执这个事情。从观测角度，实际上我们探测器探测的是你一个粒子打过来的是能动量，所以从这个角度你实际上是一个个的一个粒子，所以你从实验角度更贴切实验的 fundamental 这概念实际上是粒子 particle 的角度，这是从实验观测来说。但是从理论演绎来说，我们都开始从场建立的。这个从场建立这个，然后我们从场，然后是建立拉格朗日量，让整个这套理论程序就是大家教科书中学的。实际上现在你再回过来看的话，我们现在所说的粒子图像，它实际上就是一种在翘的 picture。onshore picture to see the quantum field theory， 而场的角度实际上是 offshore 的这个 picture。这费曼图中，费曼传播子它实际上是 offshore 的粒子，叫虚粒子。这个虚粒子概念也是非常重要的。就说这个量子效应的话，实际上是虚粒子的产生和湮灭实际上是量子效应。所以这两个图像实际上是某种意义上你不能偏颇的，是都是需要，它都有非常深刻的物理含义。但量子场论本身，我们学的教科书都是从场的概念来建立，它因为它有很多优势。但是呢，当落实到计算中，你会发现这个场的图像它就有些劣势。它劣势什么呢？就是实际上就是最关键是说规范场上，就是说规范场，我们知道光子场或者那个非 Albert 场，它是横波场，它只有两个横波自由度。但是呢，你要描述这个规范场本身，你要用 AμU 是4分量的，所以你看，为了做 offshore 的描述，你要添加2个非物理自由度，它才构成斜变的一个 我说粒子在翘，没说场在翘，场本身就是 offshore 的概念，不是这个用场来建立理论框架，实际上等效于从 offshore 的角度来建立这个理论本身。对，对，场的角度实际上是从 offshore 的角度来看这个理论本身，而粒子角度是从 onshore 的角度看这个粒子这个场论本身。所以现在这个散整幅的发展，实际上就告诉我们，我们以前都偏不到 offshore 的角度来看这理论本身，但是 onshore 的这个角度，实际上我们就某种倾向就没有 pay attention。然后我刚才说了，你为了 offshore 的描述，你要引用 A mu， 所以你研究了2个非物理自由度。那非物理自由度被添加之后呢，你肯定要把它的效应就是去除掉。这个情况是规范场是只有2个物理自由度添加，但是你要考虑引力场的话，你这个实验就更严重了。我们四维引力场也只有2个自由度，但是呢，你对称张量实际上有10个，你要用对称张量描述它有10个那个独立分量。所以你实际上添加了8个自由度，就非物理自由度。那添加完呢，你要计算物理量的时候，你要发展各种技巧，把这个非物理自由度贡献区给 decouple 掉。所以我们就会有大家非常学的规范固定，然后引入轨场等等，你就导致那个非阿贝尔规范场的这个费曼规则就非常复杂。你要引入轨场和那个轨场相应的这个费曼规则。这些步骤，所以说这些步骤的话，导致你用费曼规则去算这些图的贡献的时候，它就会有大量的容易自由度，就你中间过程会非常复杂，但是又有规范不变性，所以这中间复杂的东西它一定要相消，把非物理自由度贡献一定要消掉，这个巨大 cancellation 就导致你虽然中间过程庞大，但最后结果又非常简单，而这种就是费曼图计算的它的不有效的根本原因所在，就是你实际上绕了个大圈儿，你本身从 A 点到 B 点，你要绕了个大圈带到 B 点，那再翘角度是直接从 A 点到 B 点走个直线，这就是为什么再翘至少在计算上它极为有效的原因，就在这一点上，这个是本质的特点。然后我先把这些基本的告诉大家，然后我下面就开始真正去描述这个事情了，就描述这个给大家讲我们过去20年发展的一些基本观点。好了，这是一个开篇的一个统说，然后后面我开始进入具体讨论，大家有什么问题吗？
我来问你，就是你这里的话要给出一个更加简单的计算，
对。
但是呢，我问过你们做理论方向的人啊，你们这个方法放在那个 LHC set model 计算又似乎没有那么好的。
不是，这个是实际上是这样的，就是你会看到这个好不好，实际上是相对来说的，就相对费曼图已经好很多了。但是呢，这个最开始的发展相对规范场来它的简化是巨大的，但是你当时有质量的时候，它的简化度就没有像规范场那么大。所以说你当然有质量情况，你有时候反而是用比如标量场，你用费曼规则计算反而会简单一些。我 argument 实际上是没有提到有质量没质量，但是在这个高能中的话，实际上很多就是你在特别高能量很多粒子是可以吹得无质量的，所以在对这个精度足够情况下，很多粒子是无质量的。所以为什么它实际上是应用也是很广的，就是你用的这个没有那么好，是因为标准模型有几个粒子我们不能 treat 它是无质量，就特别是 top quark、bottom quark 还有 WZ 这几个粒子它比较重。所以在这一上它的质量贡献就会有，但是你可以通过质量展开，把它这样的话也可以 treat massless， 所以说也是有很多就是简化也会比费曼规则简化太多了，就这个是这样的一个状况。好，那我们现在第一部分我就讲旋量介绍，为什么要讲旋量？实际上这就是这个散热整复这20年研究我们实际上有个非常重要的一个认识，就是说你对你的问题要选择恰当的描述变量，就是你当这个描述变量选择恰当的时候， 你的问题就会极大简化。我们在这个载人整合过去20年有很多发展，比如这个我讲的是旋量的话，它是针对于这个是无质量粒子的描述。还有你在这个ambiguous hedron 这个里边，它就要用 moment twist 这个变量去描述，它才是很恰当的。啊 ，CH 框架它一定要用黎曼面上的这个辅坐标来描述，它是恰当的。所以说，不同的目标下，你要选择不同的这个描述变量。而我们这个标准的常论数呢，都是用这个次动量，再加上这个polarization vector 这个描述。这个呢是放之四海皆准，但它呢是隐含了，就它把一些非常重要的物理信息给掩盖掉，它没有直接满足这个物理信息。而这旋量呢，是为什么这个我们讲的一定要描述的一个东西，就是要对旋量的描述，它是对无质量粒子极为有效。而这个旋量呢，这是我们必须要是自豪的是，它这个是我们这个国内的在87年发展的这个叫 Chinese Magic 这个helicity 是variable， 它呢是非常重要的，现在大家是基本的这个一个描述无质量粒子的非常好的一个描述变量。好，这个是那无质量粒子为什么是旋量是一个更好的变量呢？无质量粒子什么？它是爱因斯坦指能关系的 p 平方等于0。那 P 点是 F 等于0，这是它两个你物理的条件。那你用这个四动量呢？你要是也写四动量的话，你的 P 平方你要变成这个是变成一个约束条件，就4个它的平方减起来等于0。这个呢是一个就是你外加的约束条件。所以说我们用费曼图计算的时候，你 P 啊在中间过程中出现，然后你最后洛伦兹 contraction 你要不停的把 P 平方或者 P 点的 F 我要设为0。所以刚开始是你没有用了这条件，你在最后结果中，你把费曼规则的 offshore 这点乘上它的外动量之后，你再去 impose 这些条件。所以这个是这个条件你没有从开始利用，这个它导致为什么费曼图计算规范上相关的很多东西，它实际上是中间表达是很复杂的原因。但是呢，你假如选择好的变量的话，这个条件自动满足。那这怎么看到这个在这个旋量底下这个条件自动满足？这个是来自于 Chinese Magic。好了。我们四动量，我们可以通过点成这个 sigma 矩阵变成22矩阵。那可以看到 P 平方的话，它点等于这个22矩阵的这个 determinant 行列式。那我们知道它平方等于0，就表明这行列式是等于0。行列式0表示什么？表明这个矩阵退化了，它不是一个自为2的矩阵，它是一个自为1的矩阵。而自为1矩阵告诉它，它就可以一定可以写成这样形式。这是变成一个列向量乘上个航向量，而这两个就是旋量，就是一个这个反旋量，一个这个旋量。那你要这个动量写成这样，在这个矩阵形上写成这个形式啊，它自动满足 P 平方等于0了。所以你用这个变量去做计算的时候，你就不再会需要去 impose P 平方等于0，而一开始用这个，它就 P 平方等于0自动满足了。这是第一个。然后呢，你在这个就是用它的时候，它自动满足条件。第二个结果呢，就是这个它实际上是这个在洛伦兹群上是0/2的基数表示，它呢它本身也是波函数，就是我们写洛伦兹的是你那个狄拉克旋让它4分量，但是4分量在无质量情况下是分成2个2的那个分量，这2个分量就是波函数，它就是朗达的 tilde， 它不是别的。所以你这一组变量，它不仅给出了动量本身，还给出你波函数，所以这就是它的一个就是一石二鸟，就一举两得。第三个，这个当然我就是这个大家这细节不需要知道，就是我这个是写的这个具体的这个2分量形式，它还有一些对称性，这个太细节就跳过。然后这个跳过这个细节，就它呢，就我们这个可以通过这个2分量组成这个洛伦兹不变的那个内积，就相当于 P 平方一样 ，Pi 点成 Pj， 它这个2分量旋量也可以组成洛伦兹不变的内积。那这个最后这个载人整分都表示成这些内积的和这个内积的这个 polynomial 或者 rational function， 它呢，它这个本身为0。这表明它实际上自己内积为0是非常重要的，而这本身也是无质量的一个体现。好了，这个呢是刚才说了，它把动量本身解决掉，这个我就往下都是这次对比你这个大家熟悉4分量和旋量的 这个标记的这个 transformation 这个细节就都可以跳过。好了，这是旋量的对称性，它的计算就是说它 IGI 这些东西，这些它的这个就是这个旋量和反旋量的内积为0，这些都是这个旋量之间它有这些关系，就是它通过这个关系你可以把很多东西变换出来，这些我都跳过去。这个当时我讲课的时候，正式讲课的时候肯定是要讲这些，但是我们只有2节课，肯定不会有这些的。而我这个讲旋量本身，实际上就是说，就是为了给大家灌输这个我是需要这个对无啊无质量的情况下，我们用黑历史对对。没有新东西，为什么是中国满级？中国满级的是新在什么地方？新在你把 P 用 lambda relative 表示，然后同时这就是我下面要说的这个第一个，你把这个次动量用它来表示了，所以次动量不再你写 P1 P2 P0 P1 P2 P3，你不再用那个了，你就用 lambda relative 它的这个各种的写。第二个就是光子的这个 potential vector 你也用这个旋量写，它就自动满足 P 点成 F 等于0。这个是用旋量写的，我当时要翻那么多页，就是为了翻这个表达式。这个就是你伽马缪它内积，然后这个是刚刚说内积，这个就是这个定义下，你把 epsilon 用这种表示的话，它就自动满足 P 点 F 等于0，你就不要外加了，你用这个表它自动满足了。这就是旋量表示的最重要的2个特点，它把这个在校条件就是从一开始就引入到你整幅计算中。对，这是极为关键的一个事情。就这个选择的这个一个意思，就是说非常好的，就是说你实际上是在这个在这个定义中，在这个 epsilon 定义中，它这个 k 是你这个粒子本身质量对应的这个旋量，就4分量的一个旋量，而这个 mu 呢是一个任意选择的 onshore 的这now 的这个 moment 对应的这个旋量分量。那这个任意选择实际上对应规范选择，你不同的 mu tilde 选择，它实际上相差这个 epsilon 相差一个规范变换，所以这个选择会导致很多很好的结果，就是你可以看到，我们马上就可以看到你这个规范变换，比如我这个 epsilon k， 这个它的 mu 和 k 的话，它自己本身它是内积为0。你这个选同样的 mu， 就是你不同的 k2， 但是同样的 mu 的话，它内积正负内积为0。但是呢，你这个正和负的时候，你这个地方这个 k 和这个 k， 就这个是它的规范选择，这个是规范选择。你选的是这个一样的话，它就是内积为0。就是量子场的里面的这个 R 线是这个 external make 是 R 线，对，那里面的 loop 并不是 R 线，对 ，loop 不是 R 线，我没必要用，我做翻译我没必要用 impose 这个对，这 inside 你不能 impose， 但是我讨论散热整复，我外线都是 onshore， 所以说。你下面会看到它为什么我这个外线这么处理之后，内线的话也会有很多简化。你先稍安勿躁。对，内线是可以 offshore 的。对，稍安勿躁，你先稍安勿躁。就是外线的话，这个东西如果你选这个，就是通过规范选择，这个 k 和这个选择一样，它就可以变成内积为0。那这个的优势什么呢？我们就考虑这个规范场，我通过这个简单考虑，我有这样的一个 claim， 就是你假如所有的粒子都是正和 helicity， 就是我们像圆波一样左旋和右旋，你可以相当于一个正就相当于一个左旋，负相当于一个右旋，这个大家光子比较熟悉的。你假如所有的外线粒子对规范场都是正的，或者只有一个是负的，那它一定等于0。就是我不需要算，我告诉它为0。不是。helicity肯定守恒，角动的守恒呢？ 对你这个说这个它为什么为零，实际上某种意义上是在那个意义上，对，从物理角度理解是这样。但是呢，我说直接去怎么解释理解这个东西？你看费曼图中，你通过费曼规则，你实际上是每个表达式它一定至少含一个 epsilon 点成 f 的因子，因为你每个传播相互作用顶角是可以带一个动量，但是它 n 点的话只有 n 减一个动量，所以说你一定n 个的 epsilon 一定要变成洛伦兹内积，说你一定有一对粒子的 epsilon I 点成 epsilon j 对必定会出现，对每个费曼图来说。那你这个出现的话，所以说这个就这个底下解释就是为什么一定会有这个因子的出现。好了，那因子出现呢，对这个地方我刚才说了，我假如选择所有的粒子的这个规范选择μ是一样的，然后我就可以通过我刚才给的这个关系，它任何同样的μ选择都等于0。因为每个图中至少出现一个 epsilon 点成 fj， 而它你通过μ的选择都等于0，那它都等于0了，就所有图都等于0，所以你都不用算就知道了。而假如只有一个为负的情况怎么呢？那就很简单，我们通过选择所有正的 h 的μ就等于 k1，那也可以通过我刚才讲的下面的关系，得到所有 epsilon 点成 fj 都等于0。就是我所有的这个正的 k 都选成这个负的这个 k1就完了，就是你一选择下所有项都为0，你就不需要算。所以你会看到这个 helicity 的这个是如何之简化，这个实际上是很简单的一个 taste 就告诉，就对 helicity 啊不是 lambda 是 helicity，epsilon 是 polarization vector， 就是我们所谓的波函数。就 epsilon 是波函数，就你极化矢量或者波函数都是 polarization vector， 就是英语就是极化矢量，也是波函数。epsilon j 是这个 I 粒子 j 粒子的这个 polarization vector， 就极化矢量，就极化矢量，对。然后 lambda 是 helicity， 就是 spinor variables。好，这是这个粗浅的这个解释了这个对无质量粒子为什么我们现在都直接用的是这个这个 spinor variables， 因为它有它的优势所在。那下面就真正进入到这个，不是，就是这个为什么这个变量在 Onshore 角度上能让这个散热整幅计算极大的简化？这个第一个叫做 bootstrap 这个方法，就是我会告诉你，我可以重建杨苗式理论，不需要规范场，不需要拉格朗日量输入，我可以重建这个杨苗场本身，从在校角度。这一节就是讲这个，对，因为其他的你实际上可以，但是我不想太复杂，我就举杨苗场例子来做一个例子，告诉他我可以不需要这个拉格朗日量，我就可以通过在校角重建这个理论本身。这个理论本身就叫这个这一节就说了，如何不依赖拉格朗，通过一些一般性原则来确定无质量粒子的散热整幅。这些分析包括维数分析、洛伦兹不变群和这些，就是利用这个一般的这个原理来决定这个理论本身。好了，第一点，我们从3点，因为相互作用最低的是从3点开始，我们开始考虑3点。3点的话，为什么在4维情况下会比较特殊？我刚刚说的这个，你可以分解成那个东西，只在4维情况下，这个高维的话，可离子里它有6维和10维可以有，但是其他的会比较就不太有。好，3点特殊什么？我们3点整幅就说 P 加 P2 等于 P1 等于0，因为它是在翘嘛。然后你可以通过这个就可以得出来 P1 点 P1 等于0。所以说你会看到呀，假如通过这个用 P 来去做这个事情的话，你看所有的 P1 点 P 都等于0。那你这个没有变量都等于0，你怎么去写出3点在翘的整幅来？你写不出来，就从这个角度你写不出来，它所有的量都为0。这个是一个原因，就是你现在实的情况下它等于0，但是呢，你看把它腐化之后，你会发现可以写出来，可以写出来。下面就是讲这个怎么在 3点的情况下写出3点在鞘整符。好了，这个困惑是这么解决的，就是你会发现通过 spinner 这个 ij 它是可以写成这样写，它变成旋量反旋量的内积，然后这是因子化是极为重要的，在四维情况下因子化极为重要的。那你知道我这个地方等于0，它只需要其中一个因子等于0，它不需要2个因子同时为0。那其中只需要一个因子为0，而另一个可以不为0。应用选择所有的这个等于0，它等于0就表明它实际上是有正比关系。这个正比关系之外的话，它就满足所有的在鞘。但是呢，整符就可以由这个方的来一个旋量，这个方的是反旋量构成的这个内积，或者选择2，就这个东西等于0，你可以用这个来表示。所以说旋量的分离是这个腐化之后的3点整符在鞘整符可以写出来的关键原因。好了，这是第一个动力学。我告诉你，这时候你腐化之后的话，因为你不是腐化的话，你这个它是，假如不腐化是实的情况是什么情况呢？实的情况是这样的，就是这个，就这个是这个的辅共轭，它是保证这样才能使这个动量是实的，它的条件。你要动量是负的话，这2个就变成独立的，这是它的一个关键原因所在。好了，我告诉你的地方是3点整符，它是一个这个唯一的，就是你通过一个唯一性，这什么意思呢？就是我们这个旋量它有这个自由度，就是你当这个 lambda 你做一个这个标量变换，它会有个 ti， 你变成 ti 的这个helicity 的这个因子出现，而这个因子这个标量的这个是一般的结论。那你可以变成这样的微分方程，就它这个等价于这样的微分方程，你这个整符作用在这个微分算符下，它一定有这样的一个东西。那这个地方你用了3点整符，你会发现3点整符的话，它一定是退化成2种情况，要么是这3个内积，要么这3个内积的这个一个函数。然后呢，你对这个东西的话，3点整符的话，3个微分方程，因为每个 lambda i 都有个微分方程。你可以3个变量，3个微分方程，你会发现它就完全确定了这个方程本身，就确定了这个函数本身。
没有搞清楚，我知道1和2是内积，但是那个大刮弧是什么意思？
什么？
这1和2这个尖的是这个因的分大，下面第2个
这个是就是1的 spinner 和2的 spinner 的内积，它是论证不变的量。
下面那个刮弧是？
这是 anti spinner 的变量。
大刮弧是内积。
这个也是内积，但是因为我说有个 lambda tilde， 这个是 lambda 内积，这是 lambda tilde 内积。所以你会看到这个东西的话，3个变量的函数，然后3个微分方程，它可以求解出来，它就一定是这样的求解乘上一个未定的系数。所以它一定这样的一个形式，这个形式这个 d 呢，它实际上是和它的 helicity 的关系就定出来了。所以3点整符，你通过这个洛伦兹不变性还有小群的这个实际上是这个都就完全确定了 up to constant。The constant 呢就是 coupling constant， 它就是3点整符完全确定了。好了，这个是当然这3点整符告诉你，在这个和等于0的时候呢，只有这个出现，只有这个小于0是只有这个出现，这个是细节，我们讲就好了。那我们现在可以对这个 h， 我们对这个 s 是这一般的helicity，比如规范场它就 s 等于1，引力场就 s 等于2，它就3点整符一定是这样的一个形状。对3个的话，它 kms 这个可能是不同的类型，因为我们知道规范场它有3个这个不同的这个生成源，所以它3个规范场。对非阿尔法规范场说，比如 SU2， 所以这个 KMS 就不同类型它的 coupling constant 就写成这样的。在这个公式中，这个细节我们都先不说。好，现在我们3点就完全确定了。对 S1 情况下，你看到这个地方有个，因为这个公式你在这个1,2，它是反对成1,2等于-2,1，它内积的话，所以你交换2个力它会产生负号。但是因为这个对规范场它是波色值，所以说要求的 coupling constant 一定是反对称的。所以这个反对称告诉什么呢？假如你都是同一类粒子，它的这个反对称条件，它的 coupling constant 必须满足对称的，因为粒子是一样的嘛，你交换它还是同，但是你要必须满足对称性和反对性，这不可能。所以唯一的解是0。 所以假如你是只有光子只有一类的这个规范粒子，它的 coupling constant 一定为0。这就是我们知道光子没有自相互作用，是不是很神奇？就我讲的是非常基本的，但是我们会推出非常深刻的结论来，就从在校的角度，就是一下我推出光子，它没有3点自相互作用，它是 coupling constant 一定为0，因为你要同时满足规范不变性，然后你这个函数本身它又要求这个它是反对称的，所以它一定为0。那非0情况呢？我们需要至少3种不同粒子。然后我们看到最小的非二倍规范群，它实际上生成源就是3个，中间没有2，没有2。我没有绕大弯子啊，我哪绕大弯子了？我没有这个旋量的定义，这是自然的，首先这是自然的。关键是你是假设了 minimum coupling 这个东西，而我这地方没有 coupling， 我只假设了。
我想吴老师说，对 R 边的规范上，对 U1 gauge field，
对，
很自然就只有 quadratic term cubic term 的 one， 还有不需要。我想这个对 R 边的场可能没有优势，对 non-R 边的场。
你后面会看到有没有优势。就是从这个角度，我这个3点整幅的确定，我只用了这个非常 fundamental 的要求，它的这个洛恩兹不变性，没有用规范不变性。不，洛恩兹不变性和规范不变性是2个不同的对称性。我这边没有 couple 费米场啊。我没有 couple 费米场，我就纯的这个规范场本身啊。然后我们在这个是实际计算，就是说这个我就跳过了，因为这个时间有限。好了，现在下一步呢，我们3点相互作用确立了，然后我就知道可以通过4点去构造4点整幅。4点整幅呢，我就要求4点的标正性，什么意思呢？就是你当这个费曼图，大家画4点相互作用费曼图的时候，比如有个中间传播子，比如这样一个图，对 pure gauge field， 对，那这个图里边有个这个东西，对不对？这个是刚才这个叶老师说的，这个动量可以是 offshore 的，但是当这个动量变成 onshore 的情况下，它的传播子是这样的东西。当这个变成0的时候，这个地方发散了，对不对？那发散之后，它的 leading 这个发散的最 leading 的这个发散是什么？变成这2个地方3点在鞘的沉积。这个实际上是任何费曼图你都有这样一个，你不管它到这个变成这个 leading 之后的话，它就这一边的一堆的这个所谓叫因子化形式，这是一般的一个结论。而这因子化形式就是树图的腰正性，就是大家这个属于。而这个实际上是这个腰正性的话，实际上是几率守恒的这个来源。所以说这个它的奇性就是这个因子化形式，就是你这个 s 等于0，就是这个 s 等于0的话，你就乘上这个传播子之后，它就可以写成这样的形式。它这个是因子化型3点。好了，我们就用3点来拼接这个东西。好，我们考虑这样一个情况。这个是2个helicity负2个helicity正，因为我刚才说了，只有一个正或者都是正的话，都是为0，所以说唯一非0情况就是2个负2个正。那它的维度4的话，它的质量为数是0，你可以写出一定是这样的形式，因为这个1、2这个因子、3、4因子是为了给它们的 helicity 恰好满足我们刚才写的那个微分方程条件，就这个因子是为了满足，就是刚才写的，它是满足这样的一个对 helicity 一般的这个微分方程，就这个方程对任何点的粒子它必须满足，所以它那个写出来的话，就是这个因子就是在4点情况，这个因子就提出来了。 好了，就这个因子是负责这样。那因为它同时呢，你又可以看出这剩下的它一定就是不是写成和离式，它一定写成 STU， 就是P 点 P 加 P2 平方，就是大家著名的这个 mass variable， 一定可以写成这样的形式。这个形式的这个前的系数呢，它是一个常数，它呢这个常数呢，我们后面会就确定。好了，然后呢，因子化，我比如 S channel 的话，因子化的话，你就可以写成这样的形式。因为因子化的话，你可以看到因子化从这个地方的话，你这个 S 出现在2个地方，所以说它就会因子化的话，它的极限的话就是 leading contribution 是这样的。另一方面呢，它写成2个这个3点整幅的乘积，你把3点整幅我们刚才算出来之后，你把它带进去之后算出来，它就得到这样一个表达式。就这些计算你不用去。那你可以考虑 STU channel 3个 channel 的这个都是因子化的话极限，你就得到这样一个这个计算过程，我就略过去。对比这个结果的话，你得到这样的一个等式。等式什么呢？这个是3点的 coupling constant 乘起来，然后呢这3个加起来，因为这2个恰好一正一负一正一负，对不对？加起来右边等于左边等于0，右边什么 coupling 写出来这个什么？就加科比关系，就是你通过4眼的这个自洽条件，你就知道这个 coupling constant 一定满足贾科比关系，它是一定是李群李代数的这个对称性的，所以你就从这个角度你就推出了它是李代数结构。没有用啊，没有用啊，我就用了腰正性啊，就是腰正性的自洽性，就导出它一定程度上别人的这个性质。就我跟你刚刚说的这个东西的话，它的这个非常独特的，简单道出很多非常深刻的结论，这个是第一个就体现。啊？什么叫 FSTU 啊？哦，这个是这样的，就前头这个地方的话，就是我刚刚说这个形式是这样的，就是第一个，你这2个是给出了这 helicity 的这个指标，然后它都有质量为数，这质量的话，它这个是质量为数为1，所以说质量为数为4，而我们知道这个它的质量为数是0，所以你底下一定是要有2个 ST， 但是你又不能写 S 平方，因为 S 平方是不自洽的，我们的费曼图里面不会有一个这个全部出现那个2次。
假如我不知道像费曼图，我只知道这个，只知道闪示整幅，我怎么知道这个 S？
你可以去加上 S 平方这种项，就是质量的话，你一定是这地方一定是2个，一定是2个的乘积。你可以加 ST 项，你会去做同样的计算，你会看到的话，这时候的话你自洽不出来，因为你 S 趋于0的时候，你用 OS 平方的话，那个项它就无穷大。
我2个动量虽然是平方是 massless， 但是我2个点积，特别是 dimensionality 特别是 correct。
什么？
我2个动量的点积不同粒子，每个人等于0。虽然 P 平方等于0，但是 P 有 PR 点去 P 界。
对，3点是一定为0，4点是不为0的，是。它是表现在这儿了，这儿，这都是啊。就这个地方，你为什么不能写 S 平方？因为 S 等于0的情况的话，它就是你敲掉一个 S， 还有一个 S 是无穷大了。对，一个无穷大了。
我就是说，不同粒子2个动量的累积，
它不等于0啊。对啊。Pi 点成 Pj 就是写成这个东西啊，这个就是 Pi 点成 Pj 的一个因子啊。好了，这个推出规范场，我们可以再考虑引力场的情况。引力场的情况 ，AS 等于2，所以给出这个它的这个质量为数是2。那螺旋度要求，这个是螺旋度要求，刚才是它们是螺旋度为1，所以 double 一下，螺旋度为2 double 一下，这是满足螺旋度的要求。然后呢，你会看到这个的一定是要，它是就是质量为6，质量为6你又不能 S 平方出现，所以你唯一出现就是 STU， 唯一出现就是这个 这样，这个因子的话，你可以确定呢，这个实际上就告诉你们4点整幅的话，我就可以唯一算出来了。这个然后呢，你可以同样的去质量维数加各种因子化，你会发现你写不出来，对 S 大于2的情况，你写不出4点的自洽的整幅来。
引力场的拉格朗日，这是量子引力还是经典引力？
这我只要求了这个场的它自旋为2，我只用了这个条件，我没说它是引力场，我只要它自旋为2，然后我通过这个自洽条件，我告诉4点，它只能写成这样形式，就它只能写成这个东西，没有其他的写法了。对。但是呢，实际上自旋为什么是引力场本身？这个时候后面你会有这个东西，我们先不说。第一个，你对大于2情况，你可以用类似的情况你构造，你会发现写不出来，就是你要满足质量条件，然后满足这个腰正性，你写不出那个东西来。
也可以用构成论质不变性的。
对，论质不变性。腰正性就是你这个所有写成这个 STU 这个论质的这个表达式一定是论质变量的这个不变量的组合，在论质不变性自动满足。但质量的条件，你这唯一的你只能写出来这个，就是对 S2大于你写不出来。这实际上就是我们比较知道一个情况，就是说实际上是证明过对这个自旋大于2的情况，这个 high spin field 实际上是我们是。对，有限还是就是对，这罗老师就写出这个结论。所以你在这个分析上，你就告诉你看到这个东西了，你分析出来这个东西。
但是如果没有引力的话，就是亚米出场有这个 high spin 的 particle 吗？没有啊 ，high spin 就standard model 里面没有 high spin 的东西吧？
没有。好。这点上，我这个地方是就把这个部分就讲完了，就是我现在通过这个已经得到一些非常 non-trivial 的结论。然后呢，下面就是这个，你说我只解决3点4点，那我怎么说我重构了这个理论本身呢？就下面要讲的就是递推关系。我通过递推关系，我可以从3点出发，可以算出任何点的这个殊途整幅。然后你要殊途整幅，你任何点算出来之后的话，那你自然是可以重构出这个拉格朗日量来，这个是我说的，我不需要从这个教科书的这个出发点，我就从这些自洽条件，我可以重构出拉格朗日本身来，就是 onshore 重构这个理论本身。啊？你必须加 infinity 的。我刚才讨论就是那你要把所有spin的你都要合在一起写成一个写成一个4点的，中间的那个传播子你必须要把它们的贡献，说要构造不同 spin 的传播子的3点整幅，然后拼接，你要把它求合起来。啊？这个你可以去这么去算一次，但是呢，这个好像没人去这么算，因为你要 sum infinity。但是这个是你要有兴趣可以去做一下这样的一个研究。对，时间到了。
控在10分钟之内。
10分钟之内。啊，这个10分钟我可能讲不完，但是我尽量控在10分钟之内。好，那下面就是什么？就是那我就是这些都是不讨论了，这个后面再说。那下面的东西，我从3点，我刚从4点的东西，我能已经得到非常深刻的结论。那下面我就要介绍，就我从3点出发，通过递推关系可以计算任何点的这个整幅，这再叫递推关系。再递推关系什么呢？实际上就是还是用的就是这个树图。我们用几个树图上，我们知道有几个基本结论。第一个呢，我们树图呢，它分母只含传播子，它是 p 平方的这样结构，所以它是一个传播子乘积有理函数。当外线中取特殊值的时候，我就说，当这个取无穷大的时候，它就分解成2个子的这个树图整幅的乘积，就所谓因子化形式。这是2个最关键的这个树图结构的解析结构，树图整幅解析结构。好了，我们就用这2个解析结构 来计算树图本身。那我们怎么做呢？我们首先第一个就是我们怎么探测这个地方什么时候这个变成0，什么时候不变成0。我给定了这个外动量之后的话，原则上你一般的外动量的话，你不会有任何内线是为0的，你达不到这个条件。那呢，我们可以做个形变。形变什么意思？就是我说这样的，我保持所有的动量不动，只选一对叫 PIPJ， 我做这样的形变，一个加 ZQ 减 ZQ， 加减的话是为了让它动量守恒。之后呢，我要求满足形变的话，它每个地方都在翘，对每个 Z 值都在翘。那你这个地方的话 ，P 方等于0，这个等于0，然后呢，要求这个都等于0，对任何 Z 值，那你就得到这个 Q 平方 Q 点 P 这个等于0。那这样的 Q 是存在的。好，这4维，因为3个条件四维空间中，好了。那这个是说这个用 Helicity 表这个 Q 是怎么写？那我们先就跳过这个细节。那现在我们看到传播子就分2类了，一类是同时含 Pi 点 Pj， 那这 shift 就不影响，因为它实际上是。那另一类只含一个 Pi， 比如 Pi 的话，你 shift 之后它就会 Z 出现，对不对？这时候你就可以选择 Z 值使得这个为0。那实际上你会看到，当这样形变之后，这个整幅本身就变成 Z 的单幅变了，只含单基点的函数了。然后这个整幅的话，我们说，我们学复变函数知道了，对一个单基点的复变函数，你知道基点位置与基点位置对应流数，这个函数本身就确定了。所以说，在校对流关系推导就通过这个大家熟悉流数定理来确定的。那怎么推导？我选这个一个维道，这个维道呢是足够大，包含了所有的单基点。那我们这个维道的话，你看这个维道积分有2个的基点，一个基点 z 等于0，z 等于0的流数什么？就 az 等于0，这是我没有形变前我希望计算的这个树图整幅。那剩下的这基点来自于 az 的这个刚才上一页写出的单基点的这个东西。那这单基点的位置我已经知道了，我知道这费曼图一定分成这个 pi 在一边 ，pj 在一边，我就知道了位置是啊。它的流数什么呢？流数就刚才我说的这个，就这个。所以说你把这个一合起来，就可以建立一个关系。所以说一边就说，所以说这个就是流数的位置，流数的这个极点计算。然后呢，这是一边你又会得到这样的一个，这个时候这个流数计算，我这个就跳过去，就得到这样的，这个 a 等于0，这个流数是我是先选一个很大的这个来计算，那另一边你把流数可以越来越这个圈越来越大，变成绕无穷远的 z 等于无穷的这个流数计算，这就边界项，这属于 B。但是呢，你可以证明对这个规范场来说，你总可以选择这对粒子的形变，使得 B 等于0。当然这个细节了，这个 B 等于0，那就可以知道，那这样的话我就知道 A 等于0就变这一堆，分成2个子的拓扑的乘积在一起的，而我们从3点知道了，可以通过3点算4点，4点算5点，5点算6点，就一直往下算下去了。这个的话，这个的图的个数增长线性的费曼图是超指数，所以说你看到这树图的话，对规范人来说，这个计算是真是迄今为止最简单的计算方案。好了，这就是所谓的，因为你选了一对之后的话，这个是选了这对就是这个这个是1和 n 是选了2边，它一定在这个图的2边，所以你一定是切成这样的 n 在一边 ，n 减1在一边，它不可能在同一边，因为这样同一边它不贡献起点。好，下面的话是不是时间快到了
？4分钟。
我这后面就是这个刚才说那个 B 那个东西的这个是更细的讨论。这个地方我规范场是可以让 B 等于0，但是对标量场的 B 等于它怎么去看这些东西的话，我们就这些都是细节就不讨论了。就这个是形变。好，我这个今天就讨论这些，下次我从这个应用开始讲起来。好。
大家有没有很快的问题吧？各位学生，我也是学生，所以这个我第一次学这个 Skype 呢，这个牙齿是长， Lagrange，我可以看 instant 这个南普这个点，你这里有你这套方法看到 instant。
我们这个是整幅算的都是微导计算了，所以说这个我们这个instant 这个非微导就在这个整幅框架里不太看得到。
这就是你的一个缺点，你们这套方法，
对，
我要比较这两个这个 advantage，还有一个就是我有 Lagrange 的话，我很容易到有限温度，因为
我刚才说了，实际上是我刚才说的是一直强调，最开始我是强调这个实际上是一个长远目标，从在校角度重构这个场论本身。实际上我刚才讲的已经提供这一点，我从这个一般考虑，我确定3点之后，我从在校地图算出任何数图点，之后我会重构拉格朗日量。那重构完拉格朗日之后，我可以讨论你的非微导的东西。
那你还是回到了拉格朗日。
但是我不是从拉格朗出发，我是从在校出发重构出来的。所以说这个时候你场不是我的第一性原理，而是在校的是第一性原理。
你的拉格朗想干嘛？你的 amplitude 算出来，你说 claim 就是说跟实验都比较了，我还干嘛要那个？
对，你这点是对的，就是说这个地方为什么我要重构这个拉格朗日量？这个叶老师的观点就是在这儿，你从咱整个出发本身你是看到非微导的东西，但是就是只看到微导的东西，非微导的东西怎么看？实际上就是你实际上说底下有没有一个框架是一个拉格朗能看非微导的东西，这实际上就这样的东西。所以说这个东西的话，我一再强调，就是我刚才也强调过，实际上是这个场论本身，在校角度和非在校角度都很重要，缺一不可，不能偏颇。但是呢，我们这个过去长期发展，实际上我们特别偏重的是在非在校角度出发，拉格朗它形式很优美，确实也应该从这个角度出发，因为特别教学生的话，但是这个在校角度的这个优越性，实际上就被隐含掉了。就我们最近发展那么多东西，你实际上在20-30年就可以做了，但大家没有 motivation， 为什么从那个角度去研究这个问题？没有 motivation， 只有最近的话，这个非在校的那个费曼图已经算不了了，逼着大家去找简化的方法的时候，发现这个角度给我们提供了很多非常独特的 deep 的 understanding， 对这个散整本身乃至量子场论本身的一个 deep understanding， 就跟我刚刚推导的，我就在校角度我就推出这个非阿贝尔观察一定是李代数的结构，这点上是非常 surprise， 我没算什么东西就推出来了。
有一个问题一直不解也许你能帮我，就是说这种，比如说我们很多班嘛代码最后都是这个是divergent，什么
对，
你的最后你级越上越这个跟实验越差越远，最后就 blow up。那个这斑马，比如说 QED， 它本身就是一个什么 toxic。
对。
那你这边
你讲的就是 Paul 今天早上asymptotic behavior. Paul have discussed this problem this morning. So students have Paul also introduced the Dyson's point of view, very intuitive observation why this is not convergent when you sum all together. But recently there have some like the not recently, in fact, this some guy did more than 10 years resurgent. This is the resurgent method. This is how to sum up this assembly series. This is then you will see. In fact, this is the series. For example, for QED, look like this. The coupling constant E square will be convergent in this regime, but after this regime, this will not convergent. So resurgent is this. I sum up this regime convergent. Then we how to analytic continuation cross this border to another regime. Then go to this continuation to this area, which is naively is divergent. So it's resurgent the method to deal with this. So that's why I always emphasize analytic behavior. Everything you should consider in complex plane. This is also another example about this, the problem you asked.
Okay, we probably need to finish Professor Feng's lecture today. So let's thank Professor Feng again.
Thank you.
So if you have more questions, please discuss him in private. And he has another lecture on Thursday. Okay, let's prepare for the last lecture today.
Sorry. Sorry.
Yeah, this is Professor Laurent Beaulieu's second lecture. He's gonna continue from yesterday's
So
lecture.
yesterday I explained the main ideas and so on. There are not so many questions, and it was only 3 transparencies for good reasons. So now I'm going to be a bit more detailed, and so these things will be, all these notes will be transmitted to you tonight, right? I understand that. So now let's go to, because remember that what we want to do, we understand that the second Noether theorem, the classical one, cannot be used to quantize the theory, because when you quantize the theory, you lose the gauge invariance, okay? So you can forget the second Noether theorem, but you have to remember it. And then you say something, there should be some consequences at the quantum level of the classical second Noether theorem that says that in a gauge theory, provided the space is Minkowskian and you have corners, you have these classical charges floating around, and not everywhere, but on the boundaries, and especially on the corners of the boundaries. So they must have an influence at the quantum level. Now, the tools to explore quantum field theory is gauge fixing. When you gauge fix, you lose gauge symmetry, but then you get something called the Beer's symmetry that says how you get rid of the unphysical modes that are created by the fact that in quantum mechanics, quantum field theory, you go off shell. And then that's why you have ghosts that you don't see at the classical level, because you don't need them because you are on shell. But at the quantum level, you go off shell. And then the ghost fields, which are still present at the classical level, couple to the theory, and their contributions, they compensate for the contributions of the unphysical mode of classical field. So it's a very deep phenomenon, of course, okay? But it's a quantum phenomenon. And by the way, if you want to look how the classical limits of that, it's rather easy, okay? So nevertheless, the quantum field theory has more fundamental fields than the gauge fields. It depends on the ghosts, also anti-ghosts, and Lagrange multipliers that allows you to impose the gauge choice that you use at the quantum level. And if you think a bit deeply, it's obvious, it's necessary. You go off shell quantumly, but you have the gauge condition has to remain, because this is the gauge condition that allows you to do computations. So somehow it's all obvious. Then the thing is that you have to understand this Noether theorem, the second Noether theorem, how it remains at the quantum level. So, but the point is that physics, due to global charges, the people doing general relativity and all that professionally, let's say, not like me, they knew what something deep should happen, and basically they had the ideas. And then Schrödinger and company 10 years ago, they say, okay, and then they got the answer. They say, okay, the S matrix should commute with the global charges, the Noether global charges. Okay, but of course they couldn't prove it. They assumed that it was true, and then they went very far, and then physically, and they say very, very interesting things. But now we're going to prove this Noether theorem. So, okay, so if you have a classical gauge symmetry, it simply means, okay, wait, I have to do something. No. Sorry. So do I go back? Okay, here we are. Oh, here are the pointer, this one. Okay, good. Made a mistake, sorry. And then, okay, so you have a classical Lagrangian, depending on classical fields that you call phi classical. And the notation will be that when I use phi with no index, it means phi classical, ghost, anti-ghost, Lagrange multipliers. But okay, now we just consider the theory depending on many fields, and the phi include ghosts and all that. And if you have a gauge symmetry for phi, it simply means that your Lagrangian is invariant under, if you change the fields phi by these transformations, where here you have a local parameter, and this is a given function, so it could be delta equal d mu epsilon, right? Then having a symmetry means that the variation of the Lagrangian is 0 modulo a derivative. It's in fact important when you play with the Noether charges and all that to say from the beginning that delta L can be d of something, right? And so on. Then the first Noether theorem says the following. It's totally obvious when you, and by the way, you also say of course, everywhere here the Lagrangian is depends on the fields and their first order derivatives, right? You could be formal and say it could depend on higher derivatives and all that, but it's totally useless because there was what happened is that you want to have good green function, so it's obvious that you must have a green function at the tree level, which is the inverse of the Laplacian, right? So anyway, otherwise you could write more complicated formula when the Lagrangian depend on second order derivative, but it changes equations of motions and all that, but it's totally formal. So we are in this case. So when the epsilon are constant, you know very well that you have the first Noether theorem that says that G, which is delta L delta D unified times somehow the generator of the gate transformations and constant ones, this current is conserved. The divergence of this current is 0 modulo equations of motions, right? So this symbol everywhere means equal modulo terms proportional to the equations of motion stemming from the Lagrangian you computed the Noether current from. So now the classical Noether theorem is useful for certain things, but when you quantize a gate theory, you don't care because indeed you need the Gauss and all that. But still, what's going to happen, and the whole trick of this derivation of things about the role of global charges at the quantum level means that we will use the first Noether theorem, that means this one, for the BRST symmetry, because the BRST symmetry is a global symmetry. You see, it has a parameter which is a constant, an anti-commuting constant, but it's just a global symmetry. So obviously, the BRST invariant Lagrangian that you have to write, that you have to derive from a classical action, it has this constant symmetry. So there is a Noether theorem, and the whole trick that will be explained here is how you write the word identity corresponding to the existence of this Noether current. And you get more information than by the other word identity that was derived long time ago. So I have to do this, I think. Yeah. Now, one believes that the second Noether theorem has more tests, more depth. And you see, what happened is that Mrs. Noether in 20, she observed that if you have a gate theory, and at the time it was general relativity and electromagnetism, not more than that, but her proof applies to any kind of gate theory, right? But at the time they didn't know supergravity, of course, they didn't know Young-Mills and so on and so on. But her proof is very good. It's a bit complicated, but it's okay. It's a magnificent proof, and actually it was really mathematical physics at the time. And then she said that if you take a gate theory and if the fields don't vanish at infinity, right? Then and the Lagrangian is invariant under the gate symmetry, then you have a current, which J mu is very useful to write the one form, I mean the J mu as by its dual. So very often the Noether current, you like to write it as a D minus one form and then you put a star. It's easier to manipulate in some equations. So anyway, that's the second Noether theorem. She said that in general, whatever the gauge symmetry is, this current, there is a conserved current, meaning that D on star J is 0, meaning D mu J mu is equal to 0. But this guy is obviously trivial because star J is D of something that is non-trivial, right? And then you have this object that floats in the world. And of course, if you compute the charge corresponding to this Noether current, you get the integration of the space-time of that guy, which is, of course, by part integration. It's the integration of this object on on the surface. I mean, you integrate this on a surface, and then, of course, this guy will survive. This guy will be integrated on the corners of the guy. Okay, it's just obvious. And then, so that's, and then when you see that the Noether current depends, of course, on this guy is the parameter of the symmetry. So it's kind of particular because you see you have a current that depends, which is parameterized by the parameter of the gauge symmetry. So you see the global charge can be written like that. So it is indexed by the parameter, and since the parameter is a function, it's a function on the boundary. It's something that is, you have an infinite number of charges here, okay, and there, and somehow this becomes something on the corners of the manifolds. So it's a very strange object. For instance, if you take, and the way you compute this charge is well defined. So if you take f mu squared, for instance, at the time she took QED, you get that this d minus 2 form is just the trace of star f, okay, which is f is just a 2 form, so it's a d minus 2 form times the parameter epsilon. But you see that what matters are the value of the parameters on the boundary, okay? So, and then it's like an index. So you get an infinite number of charge, and the infinity is related to the size of the corners. And if you do that in gravity, she did the computation, you see, say in 4 dimensions, you will get a 2 form. And you see, she did compute. Now, nowadays, we understand how simple and how geometrical are the global charges. So the value of the Noether charge for the boundaries for gravity in 4 dimensions, the best way is to say this 2 form is just the exterior product of two Vierbeins, EA wedge EB, and contracted by the parameter epsilon of local Lorentz transformations, right? It looks very simple, and you say, what is it? But in fact, you have to understand that it's just in gravity, you can eliminate the Lorentz symmetry, but at the beginning, you have a parameter for local Lorentz transformations, but then you can express these parameters in terms of the parameter for reparametrizations, right? So when you read this, you have to express E in terms of the metric. So then you have a way to express in a given gauge the Vierbein in terms of the metric. And in the same way, the parameter in this gauge, the parameter of local Lorentz transformations are expressed in terms of the parameter of reparametrization. So this expression here, in the time of Mrs. Noether, was a terrible expression, of course, where E is the function of, for instance, you take the gauge where you say that E mu is equal to E mu A, which is one possible gauge. And then you suppress the number of parameters for, so you get rid of you use completely the Lorentz transformations to reduce E mu to the metric, okay? you say that your symmetry between A and mu, it's one given gauge. And then E, in this case, is expressed in terms of G mu nu, and epsilon is expressed in terms of psi mu. And you get an awful expression, okay? And they say, where does it come from? And actually, but Nutter could compute it in her way, and without knowing actually the fact that gravity can be expressed in terms of a spin connection and a Vierbein. Okay, so that kind of things becomes very complicated if you don't go to the geometrical, to the present geometrical way to consider gravity. But under this form, you see how simple it is. It must be a two form because we're in 4 dimensions, okay? Now, you must have corners because, you know, you must have corners because you have to take the boundary of the boundary. It has to be non-trivial. So that's why you have to be Minkowski. And then you see, this guy is an obvious, interesting object if you take 4 gravity on a manifold of dimension 2. It has to be Lorentz invariant. You see, it has to be with a physical object. So basically, you have only that can appear. But a lot of geometry is hidden in that. So you have to study and to do, you have to try to get the reasoning of Mrs. Nutter and the new reasoning and all that. But you see how, you see the relation between this and this is kind of obvious for me. That's the only thing that you can write. You see, you must get this. And by the way, why is it, why this d of sat is 0 is of course because of the equation of motion, right? And so on. Anyway, so then, but then the thing is that the trouble for the last year was the following. Classically, you understand what happens, you know that they exist, but all these disappear when you fix the gauge because you have no gauge symmetry. And then, but people had a lot of intuitions. I mean, the physicists, and those, especially those knowing very well general relativity, and then they got very interesting results. But there has been a lot of confusing things because the thing that people discovered, said, and so on was very profound. And it was very hard. And also they said things in a complicated way because, as you probably know, when you go to the boundary, you have something called the BMS symmetry that says that the gauge symmetry becomes not trivial near the boundaries, okay? And part of the gauge transformations, actually, because you have boundary conditions, it's no more something which is that you can get rid of. The gauge invariance is a bit different near the boundary. And then you have the BMS symmetry. And then, of course, these global charges, they react to what is the BMS symmetry. And then you can say, okay, we have a global symmetry, but then probably it knows about the BMS symmetry, and maybe the BMS symmetry could have an anomaly, okay? And people did computations, and they found some bizarre things, right? But then, since there was no real mathematical way to handle the gauge theory near the boundary, these symmetries, because you have to know how it works with the Gauss and all that, people were believing that there could be an anomaly for the BMS symmetry. And for instance, the influence of the global charge would be destroyed by the anomaly. And indeed, relative correction do something. But happily enough, what happened, there's something like an anomaly. Now, the precise anomaly that you do, the precise way you do things with BMS symmetry as you should do, tells you that in fact, indeed, renormalization change the value of Q, but it's like a radiative correction. You see, something happened is that you have things like anomalies, but somehow it's about a global symmetry, and it's a bit like when you have a current algebra where you have anomalies, but the anomaly is very physical. For instance, that's how the pion gets a mass, right? So the very interesting phenomenon is that at the quantum level, you still have, even if you have things like anomalies, it's a good anomaly. It just says that quantum corrections change the value of the global charges. You see? Now, no way to explain that without understanding the word identities. Okay? So it's not a classical phenomenon. It's a quantum phenomenon, but which has physical effects and don't destroy the symmetry. Yes?
My question. Why here the boundary of the boundary isn't there?
Because you have a corner. You see, that's what you know. Remember when I was I hope I can go backward. Backward is maybe here. Second one.
So this one is backward. Right?
Yeah. So I want to see. I go backward here. Do I?
The second one.
No. This one?
No. This one is.
I want to go in the past.
Yeah.
Maybe it's to ensure. Yeah. Okay. This one. Okay. You see this thing. That's space-time. Okay, and then that's the boundary of space-time according to Mr. Penrose. And then you see that the boundary is sky plus, sky minus, right? But then you see that you have this thing. So you have a corner. That's what you call a corner. And then what happens is that something remains, because you see what happens. You have it. You see when you look at processes like gravitons, here they go this way. They are emitted, and here they are absorbed. And then what happens here is ambiguous. And that's why something comes from the corners. You see, for mathematicians, it's obvious. The boundary of a boundary is very often finite, but you may have complicated things that happens when you have corners that you can get rid of. I mean, this is a physical corner. It's not something that you can get rid. And actually, this was done in the 19th century because you see, when you solve the Maxwell equation by the formula, you see, you get a singularity for when you change t into minus t, and so on and so on. So that was known when you solve second order, like when you go with the Green function, okay, in with the Laplacian and so on in Minkowski space, then you have singularities, okay? And the whole issue about having global charge is because you are in Minkowski space. If you are in Euclidean space, you don't have a corner. See, it has really to do with the fact that signature is 1. You see, minus 1 plus 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 plus, so on. Okay, so that explains the thing. But she knew that, Miss Emily. They knew that very well at the time. Okay, and I think that it should be taught better for physicists. That's why I put this. I think we are here. Okay, so anyway, so that was a big mystery, and we had to understand it at the quantum level. So, yeah, okay. Now, then you have to go to the BRS symmetry because you have to add to the gauge symmetry disappears. So what is the old starting point when you are quantizing a theory? Okay, then you would start from gauge transformations. You would say that the Lagrangian is invariant, so there's a B here, of course, that went away. And then you have also this equation that is very useful because you see, in complete, and that was used, of course, by Mrs. Noether. You see, when you vary a Lagrangian, depending on as many fields as you want, and here these classical fields, gauss, anti-gauss, and B. So you know that by definition of the equations of motions, that a general variation of the Lagrangian must be equal to a term proportional to the equations of motions. So it's equation of motion of phi times delta phi and some factors, plus a boundary term, okay? And this is called, this object theta plays a very important role. And what happens is that there is a formula that allows you to derive the Noether current of this symmetry directly in terms of theta, because you see that just by, it's obvious that the variation of L, so has a term which is modulo quotient of motion is d of something, and the d of something, you call it theta. It's a d minus 1 form, and of course it depends on delta phi in a linear way. So you see what happens is that it's a general variation, and then what happens is that you see it's for an arbitrary variation of delta phi. So this piece, which is a d minus 1 form in space, is a 1 form in the space of field 1 forms. Okay? So that's where what they call the covariant phase space played a role, because in this game you will have you will have 1 forms like the dx mu, which are just space 1 forms, and field 1 forms, which are the delta phi. Okay, and then you have a kind of differential geometry which involves variation of the x and variation of the fields, right? And what's going to happen is that the Noether current, if you play with the equations, is expressed in terms of theta. Okay, and in fact, the term B, which is here, but what matters is this guy, but it will be the theta minus 1 evaluated for a delta phi, which is a global transformation for the first Noether current. Okay, so it's very well known by people in mathematics. You can explain to mathematicians what is the Noether current in physics out of this formula. Okay, and they see how it goes. All right. Now, so the covariant canonical formalism says that this delta here is more than a small variation. Actually, it's a differential operator acting on the space of fields. So it transforms a field phi into a delta phi. And in this formalism, delta phi is differential. So here you start to see an object such that delta squared is equal to 0, because delta is the differential operator acting on the fields. And what's going to happen is that the Beer's symmetry will be a particular delta. So the fact that S squared is equal to 0 as a deep property expressing the closure of gauge transformations of shell, of course, is related to the fact that delta squared is equal to 0. So the Beer's symmetry is just some particular forms of delta. See, it's a change of point of view when you do that. As soon as you realize all these things, you say, okay, out of the delta phi, I can build a measure and out of this measure, knowing functional of phi, I will be able to compute number, and then we get the path integral. Okay, and then what's going to happen is that among all possible variation of fields, you have the Beer's symmetry. Okay, so delta and S play a similar role, and then you will be somehow, if you say in my game of doing quantum field theory, if I have nilpotent operation that leaves the physics invariant, is going to be the Beer's symmetry, then I will be interested by having measures which are Beer's invariant. Okay, and then you will say, okay, a gauge symmetry means that an object like that has a symmetry S that is nilpotent. Okay, and out of that, you will say the quantities that I can compute here by putting certain operators, and operators that are determined by their covariance under the BRS symmetry, I will get identities, because S will leave the measure invariant, it will leave the Lagrangian invariant, and then you say that if S leaves O invariant, I will get something very particular, and that's how you will define physics, right? So you see, it's slow, and then and you see that on the other hand, when you play with this guy, as we do as physicists, you don't know what is delta epsilon. Delta epsilon means nothing in this language, okay? But then the whole trick is to say, I'm going to replace delta by something which is like S, and an S that plays a role consistent with the fact that you have a differential delta acting on field with delta squared is equal to 0. And then you start to say, is it really sure that gauge symmetry makes sense in physics, or is it just an interpretation that we like to because we live in a small space? What happens that when you play with the BRS symmetry, you lose. You never need to define what is a small transformation. Why? And then the notion of having a group for all possible gauge transformation is maybe not a necessity. For instance, in supergravity, no one knows if there is a group structure. Of course, we know that supergravity exists, but you don't need to have a group. If at the end of the day, what you want to compute are green functions that allows you to do measurement in the world and to compare, I don't know how a clock evolves as compared to a clock made differently, maybe you don't need a group structure, but you need something that you call a BRS symmetry. You need a path integral, and you have to define clearly what is the invariance under a path integral under the BRS symmetry. Sometimes you're lucky, and you can say that you have a group structure, as in the case of Yang-Mills. And then things like the Gribov ambiguity and so on are maybe not so, are maybe not obstructions in a certain sense. See, it's the path integral that has to adapt itself to what you define, to your definition of what is a symmetry. Now, but of course we don't work this way, and the way we proceed is to say, if you start from Yang-Mills, you try to do as Dirac told us to do, so you play with gauge transformations, and of course you say that gauge transformations, by definition of leaving invariant a given action, they must close, modulo terms vanishing equations of motions. It's better if they close off shell, but it's sufficient that they close on shell to be able to leave a physics invariant, okay? And then the point is that when you will define the action on S on the phi classical, the fact that S squared is equal to 0 is to be equivalent to this. And then there is an obvious identity, which is the fact that if you take a triple commutator and you do cyclic permutations, then you get 0, which is here, okay? Now, when Dirac in the 50s tried to quantize, in general, gauge series, he used these relations intensively, and he got lost in the complexity. And then he said, there is something wrong. See? So, what's going, so, and the whole trick is that somehow it took maybe 30, 40 years, I don't know, to do that after Dirac. Then now you understand that when we have a gauge theory, the phase space is too small if you only consider the classical fields. it goes against our intuition of physicists because, for instance, for QCD, the lattice do not need go. When you regularize and get rid of infinities by going to the lattice, you have a very good definition of Young-Mills theory. You don't need ghosts and all that. Okay, we are very lucky because it's one way to solve Young-Mills without having to. We are very lucky with Young-Mills. Of course, we cannot do it for gravity. So, in fact, the representation of a gauge theory by the classical gauge field is not a very good representation. It's too small. So the idea is to go to another representation that is made, as I was saying, by you have to postulate the existence of ghosts, anti-ghosts, etc., and then you have this covariant phase space, and then you say you change representation phi, and then you have to discover the way you represent the action of the symmetry in all these fields, and this way turns out, it was not discovered this way, but this way turns out to be a Beer's operation that you call S. S squared is 0, and the fact that S squared and phi is 0 is basically equivalent to the fact that you can associate to S gauge transformation with a closed algebra, okay? And the fact that S on the ghost, S squared on the ghost that I call C1 because that's ghost number 1, it's a primary ghost, is 0 is equivalent to the fact that you have the Jacobi identity, okay? So when you somehow you gain nothing but you lose nothing by changing delta into S as far as you have that. But then you have a new possibility, which is the fact that S squared being 0 can be done in a trivial way if you introduce a field, let's call it C bar, and a field that you call B, such that S C bar is equal to B, and SB is equal to 0, because then automatically S squared is 0 on C bar and B. So then you say, you discover the new world in the sense that you say, I start from the classical fields. It's very natural to introduce ghosts. The ghosts are somehow associated to the parameter of the symmetry, but they have a totally different interpretation. The ghost is a field exactly as phi is, which was the idea of Feynman, not in this way. And then you define the Beer's symmetry with S squared is equal to 0, and there is nothing complicated in the fact that S squared is equal to 0, because you just want to express that you have that kind of geometrical interpretation of a transformation that you change a little bit the field, right? But then you have the possibility to add as many trivial pairs, and a trivial pair is C bar B. It can have all possible indices as you wish, and automatically S squared is equal to 0 because SC bar equal B and SB is equal to 0, right? And then your principle is to say a gauge symmetry is described by Beer's symmetry S. S is a differential operator. You have this big grading with field 1 forms, so you have a delta, but also you have the fact that D, you want to do physics, so you need not only you have the gauge symmetry, but you have the points, I mean the manifold on which you build that. So you have the little d, and then you just say that S plus d to the squared is 0. And then you have S squared equal to 0 and S and d anti-commute. And you say that d squared is 0 by definition of Riemann geometry. You see? As soon as you have that, you totally enhance what Dirac did to quantize the gauge theory, okay? And quantum field theory becomes something very concrete and very computable, because from your mind has the power to say that as soon as you have delta D and S, you can define numbers by that. So you have a way to define what are the correlation functions, because you have a mapping from these complicated objects that are the fields, the way they are organized with actions of D, S, and delta, you have a mapping of these big things on numbers, complex numbers. Exactly when you have a Riemann manifold, it looks very complicated, you have topology, etc. It's any dimension, whatever you want, but at the end of the day, you have the Riemann integral. And you can compute numbers on a computer or whatever in your mind out of a Riemann manifold, right? And then the same in quantum field theory. But for mathematician, it's a complicated operation to do quantum field theory because it's like Riemann geometry, but it is infinite dimensional. See? But these things are beautiful because they allow you to understand many problems that you encounter concretely when you do quantum field theory, like anomalies and all that. Where am I? Yes. So that was here. Okay. So concretely, if you start from gauge transformations like delta phi equal R epsilon, R being a function of phi, okay, the Beer's transformation of phi is the same as that, except that you replace epsilon by C. And then you have to define, if you want S squared equal to 0, you have to compute that. So you have to find out what is C, what is SC in order to compute S squared and say that it's equal to 0. And then in the first step, you say that there are structure coefficients because there is a ghost number, right? S has ghost number 1, C has ghost number 1, phi has ghost number 0. So S, when it acts on something, it increases the ghost number by 1. So SC has to be something like quadratic in C because ghost number 2, ghost number 2. It may happen that you have new fields that will come because it's not forbidden by the formalists that have themselves ghost number 2, right? They are not predicted at the classical level. But when you do a topological quantum field theory, okay, which is a concept that doesn't make sense classically, and that was the idea of Atiyah, then Witten came, and so on and so on. Then what happens is that in a topological quantum field theory, the gauss itself has a further freedom, and eventually you have something that you call a gauss of gauss, an object which has gauss number 2. So in general, S of C has to be quadratic in C, but the framework allows you to have an object with gauss number 2. So you could have SC equals CC times F plus phi, right? And phi is, in the case, the possibility of having a phi is mathematically obvious, but then it opened the gate to a new class of theory where the theory which are invariant under such an S where you have SC equal phi plus CC, then they allow you to compute, they have observables with non-zero ghost numbers that you can compute by the path integral, just by trivial method, perturbation theory, and so on. And these objects, although you use quantum field theory method that depend on the metric, they are actually independent of the choice of metric that you choose. That's why they are called, you have observables that are independent of small variations of the metric. You see? And you cannot see that in the old language of gauge things, right? So anyway, so as soon as you say that a gauge theory is defined by an S with S squared equal to 0, you open the field to new possible kind of theories. And you can compute other things than S matrix for theories like QED and all that. Okay?
We have just 10 minutes.
10 minutes, yeah, okay. Now, I will, anyway, so you understand the importance of that. Okay? So anyway, you understand that you have, as soon as you have a gauge symmetry, you have an S, and S squared phi is 0 of shell closure, S squared C just Jacobi identity, right? And then, and now about Noether charges, which is the subject. What happens is that now you have just a Lagrangian, okay, which depends on all the phi's, C, C bar, phi classical, and B, right? I call phi A. And then the formula is that you can compute a general variation of L by the usual formula, because you have a Lagrangian, which is BRS invariant. So it's general variation is equations of motions plus D of something. And then this is your theta. But it's a theta that you call BRST1. And the only difference with the classical theta is that now it depends not only on the phi classical and their variation, but on the phi, or all phi's and their variations, right? And then you will get a Noether current, right? And then since we know now, and in, okay, let me go on. I have 10 minutes, but I think it should fit. Okay, so, no. Right. So, what we call the 1.5 is that we had intuitions, we did computations in the case of Yang-Mills, in the case of gravity, and then we observed something that somehow we had in mind. You see, take QCD, F squared, okay? The way to fix the gauge, is by the Fedorov-Popov Lagrangian, which is here, okay? I put an externally fixed B, so when I eliminate B, I get ds squared divided by 2 lambda, and this is the Gauss interactions. We all know that, right? So F squared plus this, and then that's what Tufte used to prove that Yang-Mills is renormalizable in 4 dimensions and so on. Now, the point is that these guys, it has a BRS invariance. You can easily compute that SB is 0, and SDA, SA is DC, so you S of DC, because SA is DC, is 0, and then you find easily that this is S invariant. But what is important is the fact that this guy can be expressed as an S exact term. So, in fact, the principle of BRS symmetry tells you that the gauge fix Lagrangian for Yang-Mills is, of course, classical F mu squared, which is S invariant because S is as a gauge transformation. And if you add S of whatever you want, S squared being 0, this is S invariant. So this is the case of that. And then you see the following. You see that that's a Lagrangian. It has a global symmetry S. The theta can be, it was difficult to compute it. Okay, the theta gives you the first term that corresponds to the classical Noether charge. That's for general variation. So that's the theta, the presymplectic form, right? But anyway, you have a Noether current for that because of the S invariant. And look to what it is. It says that the Noether current is D of trace of CF2. This is Noether charge, and it's a complicated computation. But at the end, you find that what comes from the red terms is an S exact term. So what we call the 1.5 Noether theorem is that, in general, the Noether current that exists due to the BRS symmetry is D of something plus S of something. So at the quantum level, you still have a charge. Of course, the charge is Gauss dependent. It depends on the choice of the gauge, But happily enough, and we say that it's a general theorem, it is under the form of S of something. So when you compute the charge associated to this current, you get the classical Noether charge, okay, and plus an S exact term. So when you compute the correlation between this charge and something physical, because the something is, by definition of being physical, is in the cohomology of S, okay, when you compute the commutator, you have integrations, and then this the contribution to this is 0, right? So what happens is that at the quantum level, you indeed have the fact that physical quantities must commute who depend on what happens at the boundary. They must commute with the neuter charges, the classical ones. It's a proof, and it is gauge independent, right? And the operator that, of course, is the obvious operator that you will choose to, and that will compute within the charge is the S matrix, because the S matrix is on the boundary. You have particles that flow from the boundaries. So this matrix, which comes from things on the boundary, has to commute with the physical charges. It's a proof. And then you have constraints, and then that's how you prove, that's how you will get, for instance, the Bloch-Nortzig way to compute the S matrix. You see, it's a very transparent thing. So now I'm going to go, okay, here, no, this way. Okay, let's go. So and then you see, and the geometrical method with the S-quantical give many examples. Okay, so so it is very clear that the conservation of the Beerest intercurrent that was not done before must be included as part of the quantization program, and a further word identity is necessary. So I'm going to, I don't have much time. Okay, so that's the form. To be very completely concrete, you see, the neuter current for the Beerest symmetry is given by this formula, which is just the obvious neuter current expression for a symmetry that in this case it is S, the Beerest symmetry. That's where you have boundary terms. Boundary terms are actually very important because they exist in gravity. You see the variation of how could I say, the transformation of the gravity of gravitational actions is the Lie derivative, so you have a boundary term, so you have to take this into account. And then this guy is a simplistic one form, theta phi of delta phi, where I replace delta par phi, and then you have, I don't have time, you have a very nice expression for this neuter currents in the space where you have contractions along the field forms. And this guy, this contraction operation along a vector field in the space of field configurations, you have a certain vector field which represents the Beerest symmetry. So for people who like the canonical, it's a very nice expression, right? So anyway, you will be. Now, the question is, how will you get the word identities for the neuter current, right? So I'm not going to go too far here. You know that in the bulk, you have the Beerest symmetry. Due to the Beerest symmetry, you get relations between the correlation functions, and you need to introduce the correlation functions of the fields, not only the classical, but the gauge and all that, but also you have to be able to do insertions of the Beerest transformation of the fields, because the gauge symmetry is a nonlinear operation, right? So there is a famous Beerest word identity that you wrote gamma equal to 0. It's the key to renormalization of Yang-Mills. But now you have to increase a little bit the formalism, because not only you want to have the correlation functions of fields and transformations and Beerest transformations of field, but you must also insert insertions of the neuter current. So you have to generalize what you do for Yang-Mills by introducing a new source, not only for the field and Beerest transformation of fields, but also for the neuter current. And I'm going to give the, if I can go in the right sense.
Can we try to reach the punch line?
Right. So that's the new word identity. 0. That's, you see, that's your action for the gauge theory with sources for the fields, Beerest of the fields, the boundary term here. And the trick is to say that you want to have sources for the Noether current of the Beer symmetry. So the whole trick is to say that, you see, everywhere you have a little d mu, you introduce a background field beta mu, which is abelian and anti-commuting. And what's going to happen if you replace derivative by covariant derivative with respect to beta, as soon as you derive with respect to beta, you get the Noether current for the Beer symmetry, right? As soon as you've done that, the standard method of getting the fact that the Lagrangian is BRS invariant is S invariant, then you get this identity equal to 0. So that's this. Out of that, so eta, see, you do, you express, you do a change of variable, which is this one where eta is a parameter, small, that vanishes at the boundary. So if you understand the way you want to write identities, you just do this change of variable in the path integral, and you get this identity. And here, eta is any parameter, it's a function of x, and then you get this. So this term is going to give you the old word identities, and the new term is a term in d eta. And when you do a Legendre transform, you get two word identities, the old one, which is delta gamma phi, delta gamma, delta v. When you invert it, you get everything that you need to renormalize. And the new word identity is this one. And it tells you that order by order in perturbation theory, every correlation functions between the phi and star j integrated on the boundary are 0. Okay? And this is this identity that will tell you, if you further integrate on x, that Q, the charge here, and the 1.5 Noether theorem tells you that it is the classical one plus S of something. So it will tell you that when these guys are S invariant, like for the S matrix, it has to commute with the Q classical here. That's it. And you have to, of course, to. Okay, I will conclude. I will conclude. Right. So that was not necessary. So you follow these things and you get this result. And the thing that, so that's, it was about anomalies, saying that you may have, when you do computation, when you do radiative corrections, you may have something that comes by one loop, meaning that the word identity for the Noether current gets a kind of anomaly on the right-hand side that comes from radiative corrections. But happily enough, this guy is always d of something, so it can be absorbed. So it may happen, and that's an interesting phenomenon, of course, that when you go to one loop, the classical Noether charge becomes renormalized. It changes values. Okay, that's a very interesting phenomenon. It's a bit like what happened when you have current algebra with the pion. You see the pion gets a mass this way. Okay, that's people interested may think to that. And all right, you see, I'm not going to explain, of course. We wanted to prove the 1.5 Noether theorem. So we said the 1.5 Noether theorem that is essential says that the charge, global charge, is d of something, classical thing, plus s of something. And we wanted to have a generic proof. So we were a bit crazy with an extremely good student. And then we said we're going to parameterize. I'm not going to do the computation, I will give you the result. You see, we took a general class of gauge of Beer symmetry. You see, we parameterize the expression of phi, which is proportional to the ghost, and maybe derivative of the ghost, like d mu c, with arbitrary functions that we call f, I, a, and so on. And then we said that we want s squared equal to 0, and then we don't know what they are, but s squared may be 0. And then we also parameterize all possibilities for s and c. And again, because of TQFT, we said there can be a ghost with ghost number 2. So we took a general parametrizations, and we just went ahead and I don't know why it's twice, but we did compute the Noether theorem, right? So now let me, I'm not going to, I will give you the result. Okay, so we impose s squared equal to 0. It's a computation. It's kind of simple. Then we computed s squared on the C. It's more complicated. That's for the ghost of ghosts. And then these constraints s squared to 0 give you 26, 27 constraints on the coefficients. It was a hard computation, right? And after that, we just use the method to compute the Noether current because we know what are S phi and SC, okay? And then we obtain this general result that at the classical level, we don't need the ghost and we recovered in general it's a different method to prove the second Noether theorem. And then with the Gates function, because the Gates function has been parameterized by a function psi, we get this result that indeed the Noether current for any theory with all these functions, we get that J is D of something plus F of something. And in more detail, it's expressed here. So for all theories now, which are such that S squared is equal to 0 off shell, that we know, we proved that indeed the Noether current is of this form, right? So I will conclude here. I could say other things. It's a brute force computation, okay? It is a complicated computation. It's very unelegant. So we are very sorry for that, but it's a fact. There should be a very deep reason that we couldn't find that if you start from a Lagrangian, which is a classical Lagrangian plus S of something, the BRST Noether current is D of something plus S of something. The fact that you get S of something, it's a complicated computation to find that it is S of something. Okay, so we checked it. It's difficult. Even if it took us 2 or 3 months to do this computation for Yang-Mills in the Landau gauge. You see, because you get lost and so on and so on. But at the end, we got the method. And gravity was worse. But then what is interesting in gravity, that's the conclusion. What is interesting in gravity is the fact that in gravity, of course, you want to do it with a Bondi gauge, because that's why it is useful to look to what happens at infinity. That's obvious why. And then the question was, how does it go in the Donder gauge? The Donder gauge is a very complicated computation, okay? We did it, and then we find some tricks which allowed us to get this general proof before. So it's very interesting, from my point of view, that whatever you say about the BMS symmetry is going to be true in the Donder gauge, for instance. You see? It's just very interesting because it's not obvious at all when you think. When you change gauge, the BMS symmetry, you see in the proof of BMS theorem, BMS symmetry and all that, it was essential to be in the Bondi gauge. Actually not. But the Bondi gauge is a very convenient gauge. It makes things easier. But the Bondi, everything related to the Bondi symmetry is totally physical. Now, why do I believe that there should be a much more elegant proof? Is that it would be a disaster. You see, it would be a disaster if we had a term which is not D exact or S exact, because then you would have problem with the fact that the S matrix, for instance, is not going to commute with the Noether charges. Okay, so it has to be true. And then it is absurd that we have to do such a complicated computation to prove that in general. I will stop. I could go further, but I will stop here.
Okay, let's thank Professor Beaulieu. Thank Professor Beaulieu for clarifying so many concepts for us. And a very short question. Is there any very short question?
Wonderful talk, but I can't follow all the details.
Of course, I'm sorry for that.
I know in the covariant phase,
space formalism, the integrability condition is a very important thing in the formalism. So in your generalized formalism,
Yeah.
does that have anything change? So
no, what happens is that whatever the gate, I don't know if I understand completely the question, but you see, when you play with what happens at infinity, especially in corners and all that, you have, is it related to that, your question? Boundary conditions?
I mean, in some special case, the boundary of your bank is not very is not very good. It can be none or so. So in some cases, the charge is hard to define.
Exactly. What happens is that you do have to. That's why Penrose is fantastic. You have to. The diagram that I showed is not to do a small drawing, which is beautiful. You really have to see what happens at the boundaries. So you have to see what are the structures of how it goes. What happens when. So you have to really understand what are the boundary conditions of the fields you have in the path integral. Okay, and I didn't go very deeply in it, but for instance, when you write the word identity, it is essential that the field transformation that you do in the path integral, it's such that it respects what happens at the boundary conditions. So this object that I call the eta of x, which is arbitrary functions, for instance, it has to strictly vanish on the boundaries because it allows you to have arbitrary whatever you want to do physics on the boundaries. What happens is that happily enough it's asymptotic. So what happens is that you take a function eta of x that says that the change of variables vanish on the boundary, but in the distribution sense. So somehow the path integral knows what happens when you do the word identity is also asymptotic, but in the distribution sense. So it gives you completely consistent computations at the end. So when you say that Q commute with the S matrix, you see it looks easy, especially when you're formal things and doing Hamiltonian things, but in practice, you see, you have to do an integration. So you have to know exactly what happened to the boundaries. But here we take that totally into account. Because you see, quantum field theory is something where computations are always done in the distribution sense. It's a passing. The path integral is just a stupid number. It's an integral. Okay?
Yes.
And it's an integration in the distribution sense.
Yes, but the problem, I mean, some problems occurs in the classical level. So,
no classical and
I don't know.
Feynman diagram, they play with distributions and all that.
I don't know the framework can help.
Yeah, sure. And then you see what happened is that, so the paper we wrote, I have an excellent collaborator in Taiwan. His name is Si Wu. Maybe, I don't know if you know him. Si Wu. Yes, Si Wu. Yeah, he's great. And then he's able to actually, these things we did with him, and he's able to understand things deeply than I do. We have different way, and he's very, how could I say, honest? Does it make sense in Chinese? Honest means he asked all possible questions, okay, and he was satisfied. And sometimes he explained me things that I should have known and all that. So what you say is a very good question.
Okay.
But you have the material here because nothing is hidden under the carpet in this. I'm not talking about this computation, which is just technical, but about the definition of the covariant phase space and all that. What is the path integral? What is the meaning of saying that the measure of the path integral is S invariant, where precisely you have to be careful to what happens at the boundaries. So all precautions are taken. And there is certainly a level of mathematical rigor which is not reached because we have infinite number of degrees of freedom. But all the words of precautions are taken at each step of the reasoning. Okay, and at the end of the day, you get a result that physically makes a lot of sense. The physics must commute with the classical symmetries, and the global charges that care by definition about the boundaries. And then, for instance, you can say we don't care about global charges in Euclidean space because there are no corners and so on. So it has to be true. Okay, and then you need a tool to do that. Now the tool is not perfect because for mathematicians, okay, young Mills, they believe that they understand a little bit, but things like supergravity, they have no way to understand. And also there's an example that I didn't give here, which is very interesting for us and for mathematicians, which is the fact is a two-form gauge field. It occurs all the time. There was, as we had before, a three-form, two-form, etc., like 11 supergravity. Is a three-form really a three-form, or is it something like a germ and all that? Because you see, you may couple a two-form gauge field. That's a good example. No supersymmetry, no nothing. You can couple an abelian two-form to a non-abelian Yang-Mills by having a curvature which is dB2. So dB2 is easy. It's like QED. G3 equals dB2. But you can add to that a Chern-Simons form. And then you get a mixing between the symmetry of the two-form and the symmetry of the Yang-Mills. Okay? That was discovered by Chapman-Menton, that you have to do that when you want to couple the supergravity time machine with super Yang-Mills, etc. Anyway, so you have objects, and then when the two-form is combined with the Chern-Simons form, with G3 equals dB2 plus Chern-Simons with the ADA plus 2/3 of A cube, you don't really know what is B2. It's more complicated than a connection. It's like when you say that mu, for mu is a one form. No, mu is a connection, which is different. A is a connection. Okay, so B2 becomes an object which is more complicated than a connection. People say that it's a gerb. Yeah, I don't know how to, gerb, G-E-R-B, right? And then you put this guy in the path integral. Okay, so, and then you have a Beer's symmetry, etc. And then you can do all this computation. But then it's also clear that there is a global Noether charge for this gerb. Okay, and then you have and then if there was an S matrix, and you can say that the two-form in 4 dimensions is like a scalar field by duality, and then you start to get very complicated things, and at some point you don't know if it makes sense mathematically, but it has to be true.
So I'm sorry, I think we really need to go. I'm really late for the schedule. So let's thank Professor Beaulieu again. So Professor Beaulieu will share the notes with all of you, and he will stay till the end of this winter school. So you read his notes. Any questions, you can ask him in private, okay? 2 announcements. So tomorrow morning, we're gonna take a group photo. So please come at least 5 minutes earlier. Just 5 minutes earlier is enough.
9 to 5. It's tomorrow at
8:55. Yeah,
okay.
8:55. And all the lecturers will have dinner together. So students, you can go and have dinner. Thank you.
June?
Yeah.